Okay, let's wait for a few more minutes so that everybody is seated in. Okay, so let's get started. So, hey everyone. First of all, welcome to this talk. So when we talk about device tree, we really think about describing hardware on embedded systems especially. And in terms of embedded Linux, Linux kernel has been the de facto source for all the device tree maintenance, where the device tree files are being maintained and where the bindings documentation is there. But what about the other projects in the embedded software stack? One of them is U-Boot. That is the most widely adopted bootloader project in the embedded system space. So how does it do with the device tree? Or it has been the consumer for device tree for many years now, but do it really maintains the device tree in a way that it should really do, or whether we do have the fragmentation of device tree when we compare the sources in U-Boot source tree when compared with the Linux kernel. So that's the things I'm going to cover as part of today's talk, and let's see the challenges that are faced by the U-Boot maintainers when it comes to device tree maintenance, and some of my recent work to reduce that burden of the U-Boot maintainers, as well as bringing device tree compliance in the U-Boot project. So something about myself. So I'm a senior systems developer at Linaro. I have a keen interest in the platform security, and that has been the part from the beginning of my career. As you could think of security, so it touches every layer in the embedded software stack, going from firmwares to bootloaders to the kernel and to the build systems as well. So I have contributed various bits and pieces everywhere in the open source, and some bits I am reviewing and some bits I am maintaining as well. And I have worked on platforms from various silicon vendors like Qualcomm, NXP, TI, Renesas, Socionext, and so on. So that's the diverse experience that I have, and I'm trying to put some of those thoughts as well alongside today. And something about my employer. So as you may be familiar with Linaro, so it is the software engine behind the ARM ecosystem. And these are the various work streams that Linaro has worked on since 2010. And collaborations is the major part of Linaro, or collaborative engineering. And collaborations with the open source communities, that plays a huge role in there. And this talk is, again, a part of that only, where I wasn't intended to work on this, but rather it is the conversations on the mailing list that led me to this talk. And so now coming on to the real topic of this presentation, device tree. This is just a primer of the device tree. I hope most of you are already aware about what is device tree. So just to reiterate that, a device tree is a tree data structure with the nodes that describes devices in the system. And the bindings documentation is actually the requirements, which says how the devices have to be represented in the device tree. And the other way to describe device tree is to say that it is describing the non-discoverable devices in the system hardware, and it's not describing devices like which are discoverable on the USB bus or the PCI bus, but rather describing devices which are non-discoverable like on the SPI bus or the I2C bus or the platform bus. And if you are interested in further reading, I have put here the link to the specifications page. You can read out more if you are interested. The second part, or the main part that is part of this presentation, is where the device tree comes from. So this is more of a generalization picture of an embedded software stack, the firmware, then which loads the U-boot, and that loads the Linux kernel and passes on the control. So where does the device tree come from mainly for the U-boot and the Linux kernel? So for U-boot, it has its own source tree where the device tree files are maintained. And Linux kernel, as you know, it's the de facto source where all the device tree are again maintained. In the U-boot tree, you would find various combinations. Some platforms import device trees from the Linux kernel. Some have their customized device trees there. So that's the real part we are trying to address as part of this talk. And there is another thing when the firmware itself tries to use the device tree. In case of U-boot SPL especially, because of the memory constraints of the on-chip RAM or the static RAM, that is very limited on the SOCs, and the DRAM isn't available at that point. So we can't really fit the full device tree onto the on-chip RAM. So instead, the device tree is stripped off, basically dropping all the non-essential properties out of the device tree, and only the essential ones that are being used by the U-boot SPL. So here you see the 3 different device tree sources being used by the different stages. Now, this usage or the different device tree sources, this leads to fragmentation as well in the device tree ecosystem. Now, the third is for the standard Linux distributions. So where does the device tree come for that? Nowadays, U-boot has been turned with the UEFI compliance so that it could boot up the standard distros. And how does it pick up the device tree? Basically, what the distro vendors do is package all the device trees for every platform in the EFI system partition. And U-boot is configured to pick up a device tree from that particular directory in the EFI system partition and pass on to that to the Linux kernel. So I considered it as a workaround for the current scenario we are in because do the distro vendor really would like to provide the device tree for all the platforms when only one device tree has to be used? And really the firmware should be responsible for passing on that device tree rather than the distro vendor. And in terms of secure boot, because I come from the security background, can we really say that distro vendor could sign all those device trees for different platforms? It's the OEM or the silicon vendor which should be responsible for signing them rather than the distro vendor. So these are some of the things that we are trying to address. So now coming on to the fragmentation sources for device tree. So this is the comparison for the Linux kernel and the U-boot versions that were mostly released on the similar dates, January 7th and January 8th. So as you could see on the left-hand side about the Linux kernel, it's the de facto source and the directories are there. On the right-hand side, there is a U-boot source tree, which has this manual DTS files imported from the Linux kernel. And the import history is very much scattered. So you could see that the import history, some platforms use the 6.7, particular RC version, 6.6, 6.5, and some platforms are currently using the older 5.15 or something like that. And some platforms may not have updated the device tree for a very long time. So this is the import history. And we can't say while comparing the device tree in U-boot and the Linux kernel whether they belong to the same hardware or not. So that is very difficult to say. And when it comes to the bindings, because bindings are not that important for U-boot to boot up the OS, they are very rarely synced. So there isn't any bindings compliance checks within U-boot. And They are very rarely synced, and if a platform vendor thinks that, yeah, I need to put some bindings in the U-boot as well, then it's there, but most of the platforms don't do that, and it's because there isn't any compliance checking within U-boot. Now the second source of fragmentation, as you could see here, this is just the clock header that I'm comparing for this Rockchip part. And as you could see here, the clock ID is being differing from Linux kernel and to the U-boot. So the real question here is, do they describe the same hardware? Can a hardware have different clock IDs for U-boot as compared to the Linux kernel? So, and if we try to use the same device tree for the Linux kernel as U-boot is using, the drivers would break because of this difference of fragmentation. The other thing about the bindings, as I said, the bindings are very rarely synced, or they are customized. So this is an example for Qualcomm device bindings prior to the work at Linaro we did. So as you could see, the UART, pin control, and the MMC bindings in the Linux kernel, U-boot had very custom set of bindings. So it is, you can say that bindings were only there for the U-boot use case, not actually about describing hardware, just to satisfy the U-boot needs. Now coming on to the U-boot maintainer's nightmare. Whenever we see a patch to import device tree files from Linux kernel, can people easily review that? Or they can say that they trust the developer that they have picked the correct version of the Linux kernel. So it's a nightmare actually for me when I was reviewing the device tree import patches for Qualcomm platforms. I was like, can I really review it? And especially if the Linux kernel source versions differs from one import to another, can we really compare what is being imported to the particular kernel version? So although we try to say to the developers that put up the Linux kernel version in the commit message, but it's really hard to confirm whether those device trees can be easily reviewed or they can be maintained going forward as well because of no bindings compliance at all. And the second thing is how U-boot maintainer should enforce the DT bindings check, because the bindings aren't synced at all or very rarely synced. And the third is, how do we bring uniformity? Whenever we say that I want to compare what device tree is being used in U-boot as compared to the Linux kernel, how do I do that? When I'm using IMXSOC or I'm using TISOC, can they really be compared with the same Linux kernel version? Can the same distro kernel can work on both NXP-SOC or the TISOC? It's very hard to say. And the other question that I have been repeating again and again, can we really boot Linux with the same device tree that is being used by the U-boot? And as part of secure boot, do I really need to authenticate multiple device trees for the same hardware? That's a big question on my mind because of my security background. We really want to say that this device tree describes the hardware, not 2 or 3 device trees which describes the same hardware. So there should only be a single canonical description of the hardware. Now, coming on to standards, the embedded base boot requirements or the system ready IR for ARM. What they say is that the firmware or the UEFI firmware should provide a canonical device tree that should be consumed by the Linux kernel. Currently, how it's done for the standard distros is like, as I've shown, they pick up the device tree from the EFI system partition and pass that on to the Linux kernel. And U-boot doesn't use that directly, but it has its own source tree for the device tree. Now, coming on to the benefits for canonical device tree, there should be a single device tree source file that is describing the system hardware, not more than one. Because it is the hardware description and has to be unique. And the main contribution can be for the Linux standard distribution, that they don't have to worry about packaging the device tree files into the EFI system partition, but rather the firmware should be providing it. And there doesn't need to be for a separate DTB to be authenticated, but rather the device tree part of the firmware should be authenticated alongside. There shouldn't be any separate need for authenticated device tree. And this has the other positive, that the reduced device tree maintenance burden, because Linux kernel maintainers or Linux DT maintainers are already putting that effort to maintain the device tree, and we can collaborate with them and maintain the device tree coherently rather than two different source trees, and there would be extra maintenance burden rather than the single place where the maintenance goes on. And the last bit is we can avoid the project-specific runtime or configuration data. So there sometimes there is this misconception that device tree can be used for the project-specific configuration or runtime data, so that we abstract out our own project using the device tree. But that device tree is not the place for that, or I would say the appropriate place for that. Device tree is really meant to describe the hardware. So where did my journey begin? So I started with U-boot, adding U-boot to the boot chain on Qualcomm platforms. Since Qualcomm platforms has this closed source bootloader, and we can't modify or replace that bootloader simply, so I started adding U-boot to the boot chain on the Qualcomm platforms. And as I mentioned earlier, there were heavily customized device tree bindings and device tree files that we had to deal with to start porting U-boot to Qualcomm platforms. So we started with step-by-step conversion to the upstream device tree bindings until my colleague Caleb took on the challenge to directly import device tree files for the Qualcomm platforms. And that actually led me to these discussions during the review with the Linux DT maintainers and the U-boot maintainers. Can we really improve the situation of device tree within U-boot? And can we make the life of reviewers and the maintainers with the U-boot community to be more streamlined for the device tree maintenance? So as I mentioned, I got involved into those discussions, and Rob Herring turned my attention to this device tree rebasing repository. So what this repository actually is, it is, you can say, an extraction of device tree bindings and source files from the Linux kernel, and they are extracted at every Linux kernel major release or the minor release candidates as well. So this motivated me to try to use these snapshots in the U-boot so that we don't have to deal with those import patches, but rather use these snapshots directly into U-boot and use them directly. So what I did was added support for this automatic import of complete device tree snapshot within the U-boot tree. And it was actually using the Git subtree that I used, and there were discussions about using submodules or using a tarball. But yeah, we finally reached a conclusion that Git subtree may be the first appropriate solution to start with, and we can further evolve it. And if there is a need, we can maybe migrate to another approach as well. And the second thing was we need to still augment the device tree files with the U-boot specific hooks, which are via this U-boot DTSI files, because we don't want to break the backwards compatibility, and we want people to start migrating and in turn reducing these U-boot specific hooks. And to make it an opt-in choice, we added this off upstream kconfig option. And along with that, we added this bindings check in U-boot. It is named on the similar thing as we have in the Linux kernel, DTBS check as a makefile rule. Because that snapshot is consisting of the device tree source files as well as the bindings. So whenever we build a device tree in U-boot, we can actually run DTBS check on that, so that whatever modifications we do in U-boot, they are compliant with the device tree bindings. So how you can run these DTBS checks? So this effort is already merged upstream in U-boot, and you can go and try it out. And this DTS upstream, this is a subtree, and you can just do make DTBS check while building your target. And if you want to just check for some subset of a matching schema files, you can do so via this command line option, dt schema files. So how the future looks like with this off upstream or with this snapshot that is taken from the Linux kernel into the U-boot. So this is the older picture, and now with the off upstream, it is using the same snapshot from the Linux kernel. U-boot would be using that, and the firmware U-boot SPL, still we need to strip down that, but it would be using the nodes from the upstream device tree file. And this would allow, if we can get rid of those custom modifications in U-boot DTSI files, then we can directly pass the device tree files to the Linux kernel. And that's what we should really aim at, and use the single coherent device tree description of the hardware. Now, when coming on to the future of device tree on ARM, so these are the two firmwares that are being used by different platforms, Trusted Firmware and the U-boot SPL. So these are providing the loaders for the initial or first stage bootloaders. So actually what I think is that the Trusted Firmware or U-boot SPL should provide that canonical device tree that is built from the Linux kernel, and U-boot should just be a consumer for the device tree provided by the firmware, and Linux kernel should again be the consumer of the same device tree file. And this would streamline the device tree ecosystem much more, so that, say for example, on a platform, you have chosen a device tree source from a particular Linux kernel version, and you know that this Linux kernel version provided device tree would work with U-boot as well as the Linux kernel, and this would suffice your platform requirements. Then you can just embed that device tree into the firmware, and that would work with U-boot and the Linux kernel. Now, these are all the positives, but there are challenges with this off upstream too. The first and the major one being, do we really have a stable device tree ABI? Although the documentation is here, but there are often DT ABI breakages that are there, and the possible reasons could be device tree incorrectly. Sorry, I need to get some water. Thank you. So the first reason can be the device tree incorrectly described the hardware. So it's a sorry case that it's an incompatible device tree change. This can be a possible reason for the ABI breakage, and the second one can be an early stage of device tree development for a particular SOC, so that there was a limited user base, and it wasn't something that was pre-thought of, that and there was a need to break the ABI afterwards because the initial version didn't satisfy or didn't properly describe the hardware. So that could be another reason. The third one could be an actual one where you want to bring the bindings compliance for a legacy DT. Say, for example, there were some redundant properties that were being used in the legacy DT, and Linux kernel didn't depend on that, but U-boot may have relied on some of those properties. But due to the bindings compliance, they dropped those redundant properties, and it breaks U-boot device tree, basically. So those redundant device tree properties that U-boot relied upon, they get dropped and breaks the U-boot booting. The last one is like just for improving device tree, maybe look and feel. There can be arguments like nobody apart from Linux kernel cares about device tree because it's maintained as part of device Linux kernel. So we really need to move away from that thinking that there are projects like U-boot that is using device tree for many years, and we really need to think about the device tree ABI. And some of the mitigations we tried to avoid DT ABI breakages is we say that we always sync the device tree snapshot at only the major Linux kernel releases or the .0 releases. And this would allow, not on the release candidates basically, this would allow somewhat stability to say that the .0 releases are more stable than the release candidates. And the other thing that the U-boot only syncs when the next branch opens, so that there is ample time for the developers to fix any breakages if there is any. And this can be a mitigation to say, yeah, they can be DT breakages, ABI breakages, and we know them, but we want to minimize them while working with the Linux DT maintainers. And we would make them aware that these kind of breakages are happening in U-boot, and going forward, we would like to reduce them. So Rob Herring is already working on this DT ABI checking tool, and feedback is very much welcome. If you think that this is part of the ABI and U-boot heavily relies on that for your particular platform, your inputs are very much welcome for this tool so that we can have this ABI checking tool for the Linux kernel. And whenever there are DT patches, it could be run and to check the ABI isn't broken via a particular DT patch or not. So this would allow somewhat a stable ABI across different projects as well. And the last one is on my to-do list. So this is a proposal that I would like to push in the Linux kernel community for a sub-arc maintainers profile, so that we can make the Linux kernel maintainers for the various sub architectures to say that U-boot aggressively syncs the device tree files, and we should really care about the ABI for U-boot. You should be asking the developers to see whether they are breaking the U-boot ABI or not, and whether their changes are breaking U-boot or not. So this is something I would like to hear from you as well, what further things you could think of that how U-boot community and the Linux community can work together and try to have this stable device tree ABI so that we can really use the single device tree description in both the projects. Now, the other challenges being, how do we handle fixes to device tree? Say, for example, after the .0 releases, there is a fix, and the next branch would open afterwards, maybe the next release. But for this U-boot release, I really need to backport a fix for the device tree. So for that, we allow this subtree to cherry pick fixes from the device tree rebasing tree, so that you can let us know, or you can post a fix. There is a script available in U-boot. You can use that to cherry pick any fix to the device tree snapshot, and we can merge that in the U-boot tree. And how do we update these customized modifications via U-boot DTSI files? Or Can we automatically update that? In my view, it won't be too much straightforward to do that. I would rather say that we should try to minimize the U-boot modifications to the device tree, or better get rid of them at all. So the properties like boot phase properties that have been accepted in the upstream bindings, we should try to upstream them more and more to the Linux kernel so that we can have the same device tree source being used in the U-boot and try to get rid of them. It's easier for all the board maintainers and the platform maintainers that they don't have to update these custom U-boot DTSI files, but rather just retest your platform after the next sync happens with the Linux kernel. And the last thing I would like to thanks all the reviewers on the U-boot community that helped me to review it, and many of the challenges that I have discussed here, they were brought up by the community only. So thanks to them. And the next steps for this journey, let's work collaboratively towards a coherent device tree ecosystem. And a special call out to the Linux kernel maintainers and the U-boot sub-arc maintainers. Can they really work collaboratively so that we have a coherent device tree ecosystem? And the last bit is let's switch to off upstream in U-boot. Try to directly use the device tree from the Linux kernel. The platforms that are already switched or they are under the process of migration, these platform listed here, mLogic. So mLogic was the first that helped me as my first test platform with this off upstream patch set. And Qualcomm is the one where we started with all the reviews. So, and Marvel, NXP, Renesas, Rockchip, TI, all of them are trying to migrate their platforms to upstream. And many of them have converted already, and there are patches that are currently under review on the mailing list. So that's all. Yeah, thank you. I'm open to questions if you have any.
You mentioned at one point device trees being like primarily the responsibility of like the firmware companies. What like I guess incentives do you see there, or like any problems with incentives or anything like that?
Sorry, I'm not sure I talked about incentives, but
you didn't.
Yeah.
No.
But I was mentioning about the firmware's responsibility to provide the device tree.
Oh, okay.
Yeah. So actually, the reasoning here is that we should really use the single hardware description, and that should come from the software that is very close to the hardware, or that's not abstracted out. So it's the firmware that is very much specific to the hardware, and we would like the hardware description to come from there. You can think of it like the ACPI that comes from the BIOS, and it is being consumed by the Linux kernel. You can't see any ACPI tables in the Linux kernel, but rather it's the BIOS which provides it. So on the similar lines, the device tree should come from the firmware. Yeah.
Thanks. How do you feel about downstream development that happens before the SOC is like upstreamed? So like for instance, say we get some hardware feature that's merged in 5.4. We push that device tree into firmware, and then in 5.6 we add support for some new hardware feature, but the firmware is not going to be updated.
Yeah, I agree. That's a real problem with the firmware updates, that people don't usually do the firmware updates. And that's a real concern, and we should really move towards, because there are these requirements that your firmware should be updatable and you should be regularly doing your firmware updates. So device tree should be part of that updates only. I think whenever you want to update your kernel, you should always consider to update your firmware as well with the corresponding device tree. That's something.
That'd be a lot of testing that has to happen if, say, firmware's kind of mature for that product. But
Yeah.
all you're doing is a kernel upgrade, and now
Yeah.
you have to go in and validate your firmware all over again. I think that might be a lot to ask for from firmware developers. So I don't know. It's just
Yeah, actually, if you take an analogy from the ACPI-based systems, you would think, yeah. So if you take an analogy, basically, we really need, because it's a hardware description. When you say that I change the Linux kernel and update or add something to the device tree, you are really changing the hardware description. So hardware description should be part of the firmware, not the part of what operating system would provide you.
I agree completely. I just know that usually there's some upstream discussion that has to happen to say, this is the right way to describe
Yeah.
how firmware, how the hardware should be described. And so, we could write firmware that has a description for that hardware, but it may not be what Linux kernel likes or what U-boot likes or anything like that. So, it's time for that to get upstream.
Yeah,
There's always going to be new IP blocks. It's not like it's
Yeah, I agree. There has to be discussions, or we really need to have a device tree that is well thought of, properly reviewed by everyone. So I know people would like to get their devices to the market as fast as possible, or the new features to the market as fast as possible. But really, we need to care about the device tree or the hardware description. We shouldn't push a device tree that is not fully baked in or that is not fully considered. So we really should push towards a canonical device tree description that is fully discussed upstream and that people accept it. So yeah.
Yeah, I agree. I just know. Yeah.
That's the tough part. I agree.
Yeah.
So I guess a couple of things, but one of them is sort of talking about the always updating the firmware, and then with your Linux, that's really hard, certainly. But it reminds me of maybe another possible problem, which is I know device tree has some forward compatibility things where you're supposed to be able to take old device trees and boot newer kernels with them.
Yeah.
The opposite isn't always as true. So when you take a new device tree, can you boot an old kernel with it? That's a different, harder problem that people don't often solve. And so I could imagine you update your firmware to a newer firmware, and all of a sudden your older kernels stop working, right? So if you have a dual boot with two different OSs and one of them you did update and one you didn't update, you could run into trouble there. I mean, I would also, I guess, sort of agree with Elliot in that, yeah, you can't, it's going to be, things are going to be broken, especially like if someone bakes their device tree into their firmware right at ship time, they probably don't have everything perfect during that first time, and it's going to be broken for a while. I mean, I guess I really applaud a lot of the stuff that you're doing up here in terms of sharing the device tree with U-boot and using it common. I still think if you're going to be in a world of hurt if you're going to take the device tree that's baked into the firmware and always use that. It feels like maybe having U-boot able to ship a device tree as a fallback if the kernel doesn't provide one, that sounds great. Because then, maybe you could boot an OS enough for it to figure out what device tree it wants. But having it be the primary and main one seems like you're just asking for trouble.
What I think really is this forward and backwards compatibility. That's the main point we should really address it. Because the project, so if you bind the device tree with the particular Linux kernel version, that's really not a hardware description. That's my viewpoint. So if you say that it's a real hardware description, then any version of the Linux kernel should work with it. I know that it's not working currently, and how Linux kernel handles the device tree nodes and the forward compatibility is not there, but we should try to move towards that. I would. So I know there are challenges, but we should try, because if you think about ACPI, I think they have solved this problem, right?
It's simpler hardware.
Yeah.
I would raise a counterpoint on ACPI. ACPI is mostly not updatable, and you will see ACPI quirks scattered through the kernel to deal with bad ACPI tables. Yeah.
Okay.
I've always said that for simple hardware, shipping device tree is fine. You want to do it for a server? Great. You want to do it for something that's like memory and a bunch of PCI buses? That's fine. But for like the complex SoCs that have massive clocks and interconnects and all of this stuff, it's really, really hard to get that right. It's hard to get that right. Years later, we take shipping hardware and we find a serious problem in the device tree that happened to work because of the weird boot timing that we had, right? And then we changed the boot timing a little bit, and trying to deal with that in the kernel and be backward compatible with old device trees is hard, and this is years later, right? So trying to do this on brand new hardware is it's gonna be really, really hard. And so I think like Chenya said, is I would say the day that you ship complex devices in the firmware is the day that someone lands the fix-up stage for the device tree in the kernel, right? There's gotta be, before you boot the kernel, before it consumes the device tree, you have a big table of, hey, someone shipped me this broken device tree, let's fix it. Someone else shipped me this broken device tree, let's fix it. And that's the day that I will accept complex device trees from the firmware, is the day that fix-up is there. So.
I think I can see the challenges with all the complex device tree cases that you have mentioned, but really, if we say that it's a complex device tree and it should be shipped alongside the Linux kernel, that's really an OS abstraction, not a real hardware description. And that's my viewpoint. But yeah,
I've submitted patches for 8650 where Linaro has maybe a couple boards, and I go test it on my board, and it just doesn't work. I have to go tweak some small setting, or we do an update to some reserved memory node. Maybe that should be coming from the bootloader and the firmware that should be telling it where those reserved memory nodes should be coming from. But it happens. It's just
agree. There are challenges, but if we say that it's a hardware description, then we should try to solve those challenges. But if we want to say that it's the Linux kernel and it's only workable with the particular Linux kernel version, this particular device tree, then it's really hard to make that abstraction out for the other bootloaders or the hypervisors as well, or the trusted OSs as well. There can be other projects that are using device tree. You can't solve that problem if you want to tightly bind the Linux kernel with the device tree and a particular version. So if we want to solve the problem for the larger audience, we should really try to solve the challenges that are currently there.
So about the backwards compatibility, it's, most of maintainers would accept it. I mean, Linux kernels maintainers. But about the forwards compatibility, I think none of the platform maintainers would take this responsibility like that. We stop the development because we want the DTB to work with the newer kernel, like to put such requirement. They will just say, I don't have such use case, I don't care, and it blocks our real development. So, people break device tree bindings, break device tree sources, not because they just don't care, although partially true, but because they have work to do. So if you are stopping people from doing work, they will kind of push back. So I think that this forward compatibility kind of is a failure. No one will agree.
Yeah, you are right. Actually, if really the point here is if we want to solve the problem for a larger community, or if we bind the device tree with the Linux kernel and we say that there are real use cases, like as Doug mentioned, that people could pass the latest device tree with the older stable kernel, and maybe different distro kernel versions would want to boot on the same hardware. Say, for example, an Ubuntu kernel, which is the latest one, or an older Fedora kernel. So there are use cases where the forward compatibility can matter and really would matter. So if you say that it's only the Linux kernel development that matters, then yeah, we are really not solving the problem for the real hardware description actually. If we
I didn't say that it's only Linux kernel development which matters, but there are different kind of requirements, and by putting the additional constraints on the Linux kernel development, you will receive pushback. I don't mind. You can create such rule, right? So just get the platform maintainer to agree on this, and I think that no one will agree.
Yeah, I agree. If we really want to move towards booting standard distros on your embedded platform, and you want to support the older distros as well as the newer distros, or the various stable kernels you want to support on the same hardware, then really you can't say that a particular distro vendor with an older stable kernel to provide the hardware description alongside that. That's a real pain for the distro vendors, I think. The hardware description, if it's meant to be forwards and backwards compatible, then really you can say that my hardware can run any distro kernel version that you could provide. So when you say that a platform maintainer could say that it's not really a use case, maybe the broader picture is not clear, or maybe the overall picture has to be clarified further, or they have to reach out to other people within the same company which cares about different distros or booting up various distro kernels. Yeah.
I was just going to add, I'm trying to think if there's a real scenario where this happens, but I think there might sometimes be hardware blocks that Linux kernel just doesn't care about. But if you want to boot some other operating system or something else, your device tree should probably describe that hardware. But we're never going to get the bindings or the device tree nodes accepted in kernel because kernel doesn't care. Kernel's not using it.
Yeah, that was one of the arguments that we discussed because the bindings should be there. The boot phase properties that U-boot uses, there is bindings in the Linux in the DT schema for that. So restricted by that, you can push all the bindings to upstream, and you should really push them. So even the kernel doesn't care because there could only be one device tree, and if you have other nodes and description that are consumed by other projects like hypervisor or the bootloader or the trusted OS, then you should push those device tree bindings to the upstream bindings, I would say. Yeah.
Christoph, do you agree with that? Is that?
Yeah, I think yes. I mean, if I understood correctly, so that the bindings for the other projects, for the things which are not used by Linux kernel, that they are accepted, but usually not in the Linux kernel repository, but in the DT schema repository. Yeah. So the DT schema itself. So the boot phase is also there, and a few others. Bindings for other cases, firmwares, Opti also goes there.
Yeah, definitely. The DT schema project where it is reside.
I think just to add on that, what I believe you're mentioning is not only the additional properties that U-boot needs about the boot phases, but the hardware that the kernel doesn't use at all, like the DDR controller or other pieces of hardware, like the firewall or things like that are configured by TFA or Opti, which the kernel doesn't really know exist. So these can't go to the DT schema repo because I guess that's too hardware specific. So those would normally go to the kernel device tree bindings. Would you accept those?
I mean, one thing is the binding, other thing is the DTS, right? So, so the binding probably should, this would be the device-specific binding. So yeah, this would go to the kernel. But it's not a problem because if you have a kernel user and the user is the driver or a DTS, then you are solved. So there's a DTS in the kernel because you will add the node and you add the binding for this DTS. So yeah.
So we're good with it. Yeah. Okay, that's it.
Yeah,
rather, I would not like to have the binding where there is no kernel user because then you don't know who uses the binding.
Yeah, the user in your definition is a DTS.
As well, yes, yeah.
And you're okay with the DTS that doesn't have any, like, compatible that kernel doesn't care about? Or
Yeah, so there are DTSs which they don't have any driver which binds to them. There are such cases, so this was accepted, right? It's not ideal, but if there's a purpose like here, then it makes sense.
Yeah, actually, that's something I had some thoughts about it earlier, as you did. So that was clarified with Rob and Christoph during those mailing list conversations. Yeah, really, we need to have the single device tree binding source, and where all the bindings corresponding to hardware can exist. And I know there are DRAM controller specific bindings or DTS nodes that are being used by U-Boot as well to configure the DRAM controller. I would also be in favor of pushing those bindings upstream too, so that we can try to minimize those as well and have a common device resource. Yeah. And have those discussions with the upstream DT maintainers. Yeah. So, is there anything else you would like to question, or are we done? Okay, thank you everyone for patiently listening to me.
Ah. Ah, ça marche. You don't hear me? Attends. You hear me? Yes? I wait for something? Okay. Hello. Sorry?
Do you have any audio in your presentation?
Audio?
Sounds?
No, no. No, just me.
Thank you.
Let's go. So, hello. We are going to speak about suspense RAM in, let's say, complex SoCs for automotive. So first, I'm Gregory Clement. I'm embedded Linux engineer and trainer at Bootlin. So at Bootlin, we do embedded Linux, and it's our expertise. We do development, consulting, and also training. And we have a strong open source focus. On my side, I contribute a lot to the kernel. So mainly on the Armada SoCs, and I'm still a co-maintainer of this subarchitecture, but I also work on bootloaders, and currently, for example, I work on another SoC from Mobileye, and I live in France, near Lyon. So the main use case we have that led us to implement suspense RAM is to have the car ready immediately. Usually, what we hope is as soon as we open the door, then we can use the car. And usually, we don't want to wait for dozens of seconds before being able to start the car, or even before being able to open a door. And actually, it's not only the case for the car, but also for any consumer device. People don't like to wait even a dozen of seconds. But in the other end, complex systems require more time to boot. There are a lot of things involved, a lot of things to start, many cores to synchronize, and so on. And that's why it's not so easy. And but thanks to all this complex, to the fact that people really want to have it ready, manufacturers are ready to spend a lot of money to allow us to work with this complex SoC. So how to achieve this, the fact to have the car ready when we want it? One first solution is to reduce the boot time. So we have some multiple fast boot solutions, like, for example, the Falcon mode of U-boot, or we can use GMA to load the system while doing something else on the CPUs. There are a lot of things available. There are specific talk about it at ELC now and every year. And actually, my first talk 15 years ago was about how to how to boot fast. However, these solutions are very efficient, but only until the first init process. Then, and especially for automotive, we have in user space a lot of containers, graphical framework, and other big stack, and all of them take a long time to be initialized and load and so on. So another option is to not boot at all, but just suspend your system, and then, so that from the point of view of the user space, when the system is suspended, nothing happens, so you don't have anymore to initialize anything. Everything is ready immediately as soon as you exit your suspend state. But with suspended RAM, there are still some challenge to address. First, we need to ensure the integrity of the memory, because when we are going to go to suspend RAM, we want to be sure that the memory won't be corrupted. And we also want to be sure to restore the hardware in the same state it was before going to suspend. Another thing we need to address is the power consumption. We want to consume as little power as possible, because if at the end we consume as much as a normal state, there is no point to go to suspend. And the purpose of going to suspend RAM in this context actually is to just be able to let your car shut down, or like shut down, and then be able to have it in as long as possible. So you need to consume as minimum as possible. And the last thing we want to achieve is to be able to doing a fast resume time. And unfortunately, it's hard to satisfy these three items at the same time. So we need to find the correct balance between all of them. So what we are going to see during this presentation, first, I will present the hardware of the DRA 821. It's a SoC from TI that belongs to the Jacinto family. And there will be a focus on the firmware and the hardware that are involved in suspended RAM. Then we will see how we implement suspended RAM support for this SoC. And finally, we are going to see the challenge and the improvement we can do. So let's see. So here it will be a really overview of this SoC. So the Key3 family is a multiple core SoC architecture platform. So you see we have a lot of cores there. Let me. We have a lot of cores there, there, and there. It's designed for low power, high performance, and high integrity device architecture. And Jacinto is a part of the Key3 family, but that targets automotive. And now let's focus on the multi-core processor for this SoC, because that's a part of the complexity we will have to face for suspended RAM. So what we have there. So we have two Cortex A72. They are ARM 64-bit. They belong to the main domain, so it is all this one. And they are running Linux, TFA, and U-boot. Then we have two pair of Cortex R5, so one on the main domain, the other one on the two other one on the R5 domain, the MCU domain. Here we have the DM firmware that is running, as well as U-boot and also some custom firmware. And finally, we have the Cortex M3, which is called here the MSC, which belongs to the wake-up domain, and it's there that we have the secure firmware that is running. But for suspended RAM, not only the SoC is involved, we also have two components that are very important. The PMIC, so Power Management IC, which powers the SoC and the DDR. And it will also handle the wake-up when the SoC will be in deep sleep or even completely off. So it's the only component that will be able to capture any wake-up event. And depending on the hardware design, there might be one or two PMICs that are involved. The principle will remain the same, and just some implementation will differ, but for this presentation, we can consider that we have only one PMIC. The other component is the DDR. It's need to be programmed to maintain its data while no longer being driven by the DDR controller. And also, when the DDR is in this state, it allows to consume less because the frequency also of the refresh can be lower. We have several low power modes that can be used on this platform. So we have the active mode, which actually is the normal mode. In this mode, all core are all the core and all the power domains are power on, but it's still possible to do some power management action because in this case we still have runtime power management, DVFS, AVFS, CPU idle. So it's even in active mode, it's still possible to save power. We also have the MCU mode. So in this case, it's the main power domain that is shut down. So that means the A72, so with Linux on it, and also, if you remember, the two other MCUs that will be powered on. And not only the core, but also all the controller that belongs to this main power domain will be also off. Actually, these two modes were not used for suspend RAM. It would be possible to use MCU mode, but it's not the thing we work on. And obviously, in active mode, there is no suspend RAM. We have then advanced low power mode, the one that we use for suspend RAM, the IO retention mode. So in this case, the entire SoC is off, excepting a very small part that will manage to capture the GPU, the event of the GPU of the SoC itself, to then being able to exit from suspend. So, if we have time at the end of this presentation, I can give more detail about it. And we have also the off mode. So, in this case, the SoC is completely off. So that means that the PMIC is the only wake-up source because we shut down everything for the SoC. So now let's see the normal boot sequence, which is not so simple. First, I will mention two important parts of it. The TI foundational security, which I'm going to call it TIFS. It's responsible of managing the hardware firewall. So that's these components that will allow to a CPU to access some controller or some part of the memory and given some policy. And it will also control the CPU themselves. So it this component that will allow to start a core, stop it, set up the reset vector, and so on. Probably can do more, but for suspend RAM, that's the part that interests us. Then we have the device manager firmware. So this one manage a lot of devices, and among them the clock and the pin control. So they are all centralized there, and the idea is that every time you want to manipulate a clock, everything goes through the DM firmware that allow to have multiple firmware at the same time and still have a current state for the clock and the pin control. And the communication to DM firmware and TIFS is through the TI SCI, so it's an API that allows to do the communication. Actually, even when you communicate, you send everything through TIFS, and then either TIFS just do the service you ask, or just forward it to DM firmware. So now let's see the boot process, the normal boot process. So at the beginning, we have some code in the ROM that is executed, but what interests us is the very beginning, what happened in R5. So here, this ROM code. Okay. So this ROM code will first load sys firmware. So typically here is TIFS, so it will load it in the Cortex M3. And so this one will be able to provide the service we want, and so control the hardware firewall and so on. It will also, the Rockwell will also load and execute U-boot SPL, but U-boot SPL that have been compiled for the R5. So this U-boot SPL will then will load the TFA in memory. It will load the DM firmware also. And then it will, at the end of the process of the boot, it will request TFS to start the TFA on A72. And once it's done, the last thing it did, it will jump into GM firmware. So the code in R5 will initially run the U-boot SPL, but then U-boot SPL is just discarded, and what will continue to be executed is GM firmware that remain in memory. And in parallel, we have TFS that are going to run in secure world, and then it will execute U-boot SPL, but this time in A72, that will in its turn run U-boot, and finally we will be able to run your Linux kernel and your full system. So now what we are going to see is what we have done to implement suspend to RAM support for this SoC. So first, let's see the overall sequence. So I will describe it now briefly, but then we are going to see each part separately. So let's go. What happened? So we start from Linux because it's from there that we receive the suspend request. So in Linux, we do a suspend request. So typically, we do echo mem in /proc suspend. Proc memory. Then, so here we have the normal flow. So Linux will call the suspend handler for all the driver involved, and at the end, it will just perform suspend request to TFA. So this part is pretty standard. Then TFA will execute itself normally, but something which is start to be specific for our platform is that on our platform, TFA is executing from SRAM. And so when the SOC is off, then the SRAM, which is part of the SoC, will be also completely off, so we will lose the memory. So what TFA do is save its context in somewhere in DDR. Then it continues, and at a point, it asks DM firmware to put the system in suspend. So at this point, so when we switch to DM firmware, so the Linux doesn't run anymore, and TFA doesn't run anymore, so we wait with WFI at the end. So now the DM firmware is the last man standing, which is executed in Cortex R5. It copies the important part of the last part that will be executed, it copies it in SRAM. And then the sequence here is to first put the DDR in self-refresh, so in a way that it will be completely autonomous from the DDR controller. And it will also write it will write magic number or a flag in a PMIC register. And finally, it will ask the PMIC to shut down everything, excepting the DDR that will be maintained at the low voltage. And then the SOC is off. So when we wake up, the wake up can only occur on the PMIC because the SOC is completely off. So the PMIC receives the wake up, then it will start the SoC, And at this point, from the point of view of the SOC, it has a cold boot because there is no way to know that it is a resume. So we have the same sequence that we saw just before. So the U-boot SPL start to run, but at the early beginning, U-boot SPL will read the specific register in the PMIC to look for if there is a flag that we put there. If the flag is there, that means actually it's not a normal boot, but just a resume. So in this case, instead of, maybe I didn't tell you, but in this whole sequence, it is the R5 SPL which is responsible to initialize the DDR. And so in this case, we are not going to initialize the DDR, but more exiting the DDR from self-refresh. So from this point, instead of like in normal boot, loading everything, in this case, we are going to load, instead we are going to load TFA and DM firmware from the storage, like the normal boot. And then, so we continue to execute DM firmware. We jump on TFA, but on TFA, and before jumping on TFA, we're also going to write some information in a register of the SOC. And so in TFA, at the early boot, we are going to check this register. And if we have the flag that indicates it was a resume, we are going to restore the context that have been saved, and then we are going to jump in the resume function, and then we go back to Linux, and that's all. So now we are going to see each software more in detail. So for Linux, the sequence is a standard, and it is done through TFA, so nothing specific. There are still some things that have been done specifically in our case is for each driver level, because generally the assumption is that the controller is not completely off. We expect that we'll lower the power consumption, but there are still some configurations that are still present, and in our case, it's no more the case because it's completely off. So that's why we need to save and restore the register value or the configuration. So we need to put it on a part and then restore them. And another thing that also happen is usually there are some devices that are initialized only one time when you start your system, and then when you go to suspend, they still remain in the same state. Typically for PCI, when you go to suspend, your PCI bus is still there, available. But in our case, it's no more there, and you can't make the assumption that it was only in the good state. So you need to perform a reset sequence that normally you don't do when you just go into suspend RAM. So that's the thing we need to take into account because of the fact that the SOC is completely off, but it really depends on each driver. For some drivers, they already save all the context, or for some driver, actually you don't really need to restore the thing. So it has been done driver per driver. The next one is TFA. So by default for this SOC, TFA reside in SRAM. It's possible to put it in DDR, but in our case it was in SRAM. And as SRAM and DDR are possible, we also need to take care of this specific solution. So as I explained, when the SOC is off, the SRAM data is lost. And so what we need is to save and restore the TFA memory. So in our initial implementation was this one. We just completely copy the full SRAM at the place. And then during resume, the EU boot just copy back the SRAM state. And so we can just reuse the entry point that exists in TFA, so that to detect that it was a warm reboot. And so the only thing we need to do is to store the resume address during suspend and pass it during resume. But actually, there are some issue with this. Initially, there was no issue with it. But then the way TFA and the U-boot manage a firewall change. So actually, there was not really firewall around TFA, or they are not really applied. But now it is the case. So that means that, and how it is done to be in a secure way is it is TFS that manages the firewall, and to ensure that what you are going to put in a secure place, TFS need to load image with a valid signature. And so how it works, you load, yes, more or less, load the image you want through TIFS, and once it's loaded, then it will apply the firewall around it. So we can't anymore use the image we have, because the image of the memory we have, because it can change, and so we can't sign it at runtime. So that's why finally we each time we resume, we load the initial image that have been signed. So it's recognized by TIFS, and so from the point of view of the firewall, everything is okay. And that's why we, at the beginning of TFS, then we restore just the context that have been saved during the suspend. Yes, so that's what we have here. Now let's see DM firmware. So this one is the final software that is executing before the SOC shutdown. So what DM firmware will be responsible of putting the DDR into self-refresh to maintain integrity, and to send the sequence to the PMIC for power management. So yeah, two things. To first shut down most of the power rail to save power, and so usually we just have one rail that remains for the DDR, and the one that is with a low voltage. But another thing we need to prepare is to declare which of the GPIO of the PMIC can be used as wake-up source. And actually, we only manage GPIO, but it's also possible to use the RTC of the PMIC or anything that is part of the PMIC. We had to move the code in SRAM because at the very beginning, I hope that when I execute the code, everything remains in the cache, so it's okay to put the DDR in self-refresh like this, but it's not enough. So we need to put everything in SRAM, so we are sure there is no more any access to the DDR while we ask the DDR to go in self-refresh. And after this, the last thing to do is so we store a magic number in the PMIC. So it's because there was the need to know when we resume that it was a resume and not uncall boot. So we need to put the information somewhere. The SOC being off, the only place we can put something is the PMIC. And fortunately, there are some scratch register in the PMIC, so you can just write something like there here and read it back. Initially, we also put the TFA resume address at a known place in DDR, but then, of course, it was no more the case with the new implementation. For the resume part, actually, there was no special adaptation because when we resume, the firmware is not resume; it's just booting like a cold boot. And for this, the prerequisite was that the device that had managed by DM firmware was deactivated by Linux during suspend. And so that means that when you go back to Linux, then Linux will take care of to resume all of them. So we don't need to maintain any information inside DM firmware. All the context, the device activation are managed by Linux. So that, as I said, the DM firmware boots normally, and there is no additional step needed for this one. The last part was U-boot SPL. So here, obviously, there is no change during resume because during resume there was no more SPL that is running, so it's not involved. But SPL is involved during no, it's only used during resume and is not involved during suspend. And so during resume, it's at the very beginning. So the role of the SPL is to detect, to access the PMIC and to detect if we came from a normal boot or a resume. It will also do the opposite of what was done by DM firmware, so it will exit the DDR from retention instead of configuring. Then it will take care of reloading TFA and DM firmware. So initially, so as I said, initially we restored the full SRAM from DDR. Now we reload the initial image to ensure that it was recognized by TFS, and then it can apply the firewall around it. We made some optimization. Is that actually during boot, during resume, instead of reading back DM firmware and TFA from the storage, so in our case it was from eMMC, no, from SD card. We just during normal boot we just keep the copy of them inside memory, and then we reuse them directly from the DDR and no more from the storage. So that's what we managed to do, but actually we found some issue and also some improvements. There are some improvements that are still to be done. Some of them have already done. So something I did not mention is actually we need to ensure globally that when we are going to suspend, as we need to be sure that every information that was in the cache will be flushed in the GR, because as all the core will be shut down, then the information in the cache will be lost. So we are be sure to synchronize this. So we ensure it for L1 and L2 cache, because actually it was easy, because it's part of the ARM implementation, so there are standard way to do it. But the L3 cache is managed as SoC level, so it's not at the same. So it's really for each SoC vendor that they have the way to manage it. And actually, our initial implementation to avoid this issue was just to completely disable the L3 cache. So not only for suspend, so for the full system, there was no L3 cache available. But then we still wanted to be able to use it. So we need to access them, but initially the access to the registers that manipulate the S3 cache was firewalled by thieves, and so we wasn't be able to use it. So it was needed to make some change in TFS to allow GM firmware to access this register in order to disable the cache just before going to suspend. And then when we resume, the cache are enabled again. Yes. And when we disable the cache, automatically the SoC flushes them to the DDR, and that's what we want to achieve. There are some other things we didn't realize at the beginning because we are really focused on being able to do suspend RAM, so it works well. But there are some security weakness when with what we have done. And it's we have some feedback from the TFA developer when we submit our solution. And for example, from the point of view of the TFA developer, the SPL image is not trustable. So even if I didn't mention it, but when we boot, everything is signed and is checked by each component. So we have TFS that checks that the SPL image is signed and so on. So normally, all the things we have are safe, but from the TFS standard, the code in SPL is not safe enough by itself. So, and there are some concern about the fact that even the context of TFR was accessible during resume because we put it somewhere in DDR, but there, in theory, there is a slot during time when just before TFA was executed, so at the beginning of the execution of SPL, the memory, the context of the DDR is readable by everyone because the hardware was applied too late. So one solution is to encrypt TFA during suspend. So it's allow two things. It's allow the confidentiality, so no one can be able to read it during resume because it have been encrypted while actually the part of the memory was already firewalled, and when the part of this memory is no more firewalled, it is encrypted, and so it is encrypted, it also ensure the integrity of the data. But for this, we need someone to do this, and so one solution chosen was to use TFS as encryption-decryption agent, but that means some change in TFS to support this feature. But we can't. TFS, as it is, it's very simple things, and when you boot, it's the normal TFS that is boot, and TFS is not aware of the fact that we resume or not, and it can't do it easily because first, when it boot, the DDR is not available because we didn't do the sequence to exiting from retention. And also, in TFS, we don't have access to the PMIC because that means we also need to implement the A2C support and a lot of things. So that would mean a lot of things inside TFS, so DDR management and PMIC access. So a solution for this was to keep SPL to exiting the DDR from retention and to detect the fact that you resume. But in the same time, and TFS will still decrypt TFS. So the flow now, or not now, what the flow would be is we exit from resume, we exit the DR from retention, and then SPL will tell TFS, so now it's resume, and it's TFS that will automatically decrypt the TFA, and at the same time apply the firewall. So it's safe, and then you can go back to your normal execution. So that means a collaboration between SPL and TFS and a new set of call. Yes. There are another things we didn't address. If you remember, I said that in R5 core, there is the DM firmware, but you can also put some custom firmware. And until now, they were completely out of the scope. And but we need to manage them during suspend and resume. So there is two options actually. So either the firmware take care of them themselves. So they free and stop the device during the suspend. They restore them. They also, if needed, each firmware will save data. If they use some SRAM, they save it on DDR. And so that all this firmware will need at the end is just a notification that you are going to suspend, and then it should take care of everything. Another alternative is to that the firmware will be completely unaware of the system suspend, and in this case, that would be another component, so typically the DM firmware, that will take care of all the device management, and but that means that we'll need to have a way to restore the firmware context when you resume from suspend. And that's for the firmware themselves for the state. But in both cases, we still need to manage the link communication. So when we exit from suspend, we need to restore the communication channel with this firmware that is running to be sure that we can continue to talk with them. And finally, actually, DRA 821 is not so unique in Keystray family. So initially, we thought that the other SoC of the Keystray family do the same thing. So they also completely shut down the SoC. Actually, it was not the case, so that's why we had to create a specific solution. And because most of the SoC don't use off mode. But now the plan is that some of other SoC can also use this off mode. And also, in general, we still want to have a common code with SOC that do off mode and SOC that do higher retention, for example. So now the ongoing effort is to have a common base for everything, and that will manage the SoC that shut down everything and the SoC that still have high retention. So that means to have common code in TFA, SPL, Linux. It's just the DM firmware that can remain specific for each SoC. So if you have some question. Yes. Okay.
Do you have some numbers on power consumption and how much you save by going into off mode instead of IO retention mode?
Okay. Actually, it's quite the same thing. We made the comparison, and There are some differences, but compared to the power consumption of the full board, because even when you're going to full suspend, or even if you use the PMIC to shut down everything, there are still some components that consume power. And the difference between high retention and off mode is not significant, but sorry, I will show you something. Yes. Where I am. No, not this one. So I will do it in a different way. So just to explain you something which is specific to, okay, this one. It's not. Because the higher retention mode for the DRA is different for the other one. Here, what we maintain is only this here, for the same for the two main domain, but it's just a very, very few part of the SoC. We're just here to capture a GPIO and then forward it to directly to the PMIC, and that's all. So there is nothing else. So that's why the consumption is very different. So here the high retention mode is just allow to, instead of using GPIO from the PMIC to wake up the system, you can reuse some GPIO of the SoC. So that's why in the end the difference is very limited. I don't know how it works for the other SoC like Citara, because for this one, for now they only implement high retention mode, which is way easier to implement because you can all the things we do with the PMIC or the fact we have to switch between SPL and TFS and so on. Then if you can keep the information, it's easier.
I was going to ask, our alternatives are what, suspend to idle and just shutting all the way off. Do you have comparisons, like for power and time to resume?
For power consumption or for resume time?
Yeah, power consumption and resume time. I mean, those would be the metrics that you mentioned.
For power consumption, there is a lot of difference because in suspend to idle, the control are in low consumption state, but they are still there. For example, at the point there was a need to be able to use there is a kind of switch that is embedded in SoC, so we need to route the packet during suspend, and actually this one was part of the main power domain, so everything was there. So we just go into suspend to idle, and here if I remember, but the consumption was closer than the active mode that so there are a big benefit to going to suspend to RAM for this one. But of course, in suspend to idle, the wake up is instantaneous because there is nothing to it. There is no all the full boot process that we have.
Right. Okay.
Thank you. And
Right direction.
This looks so complicated. It's actually more like hibernate than really a suspend.
yes. Yes, but
Well, but in Hibernate, you suspend to disk, which is
Yes,
much
that's
slower
what-
to read from than the RAM. And the key difference is you have to keep the RAM in self-refresh in this mode. Whereas
actually, this kind of thing I've been done in the past. I know that there are few others. There are some earlier ARM SoCs that when we do this, when we go to suspend, actually we keep the RAM and everything was shut down, and it was the same thing. It involved the bootloader to detect things. Usually, what we do, we have some pattern in the RAM. Here, the thing that is more complex is the fact that now we have all these secure things that add extra step that we didn't have in the past.
So with all those extra security steps, do you realize a boot time performance still with suspend a RAM? What is the boot time improvement with this technology?
Improvement of what?
What is the boot time improvement?
Okay.
Suspend a RAM?
I think we. Let me think about the. It was. I think we managed to boot in. To resume in less than 2 seconds. And the cold boot, actually, I don't have access to the full cold boot of the real things, but even the normal boot without all the stack, it's I think it was around 10 seconds, but it's without all the stack I mentioned. And so when you start to add some container and stack and what I don't know for this particular system and this particular SoC, but for other one, I know that usually it can take until 30 seconds just for a normal boot, and so yes, we save a lot of time. For now, we didn't put many effort to optimize it. There are some improvements that can be done. But yes, we didn't. But we did first one. I mentioned the fact that we don't read anymore the eMMC, so we can have it directly. And then that's all. But yes, it's a couple of and then the things that take time actually is out of our control. Is it depends on the boot media. It depends on what is done with the secure part before. The fact that we have multiple ROM codes that are executed before then being able to do something. So that also something we can improve or can be improved, but it will also need maybe some hardware change. So for example, we notice that depending of the SD card we use, we can save a few seconds. So it's huge, but maybe I know that we can boot with Spiner, so maybe it's faster for eMMC. That all the things I didn't work directly on it, but that's some improvement we can do.
Thank you. Thank you. Another question, was there any consideration given to ECC-backed DDR, error correction coding, for the suspender RAM to kind of ensure the integrity if there were any accidental bit flips due to noise or anything like that?
No, I'm not aware of it, but I don't know. I don't know if the controller can do it. Oh, yeah.
It's something that happens at configuration. So since you're not changing it, inline ECC will still be active. Then so it should be secured.
Thank you.
Okay, so we're done. Thank you. Phew.
Okay, I guess we can get started. Okay. Okay, hello everyone. My name is Sudarshan. I work as a Linux kernel developer at Qualcomm. So in this talk, we're going to talk about one of the methods to reduce boot time. Since I think in the previous talk we were talking about boot time reduction, and this is one of the flavor of it. So the topic is called deferred memory block initialization for boot time reduction. So in the agenda, I'll talk a bit more about me and the team, what we work on, and what we are in Qualcomm. And I'll talk a few functions related to memory, system memory initialization, like paging init, bootmem init, and then init. And we'll talk about the deferred memory initialization, and then ways to limit the boot memory, and then what is the boot time reduction KPI numbers, like what are the performance numbers, and then the challenges and the limitations with this feature. So I work in the Linux kernel team. So we majorly do memory management, scheduler, DCVS, board bring-ups. We are like the core kernel for most of the kernel features that we do, for our Android OEMs. And my work is majorly in the memory management side, but I also have interest in firmware, system architecture, and system designs. And we are hiring, just a side note, to expand our team. And if anyone of you are interested to join the kernel team at Qualcomm, do send an email to my email ID, which is in the intro slide, and or we can talk in this event. So something about the paging init. So paging init is like a foundation of the memory management in the kernel. So when the kernel boots up, it's going to call the paging init. Basically, it sets up the page tables for the entire RAM or the DDR, and it's part of the start kernel routine. When your kernel is starting up. But the interesting thing is all this initialization of the memory. It's all done in the boot CPU using in a single threaded fashion. This happens even if you have an SMP system, like if you have multiple cores. But the whole boot procedure happens in the boot CPUs, and most of the time, in a big, little, or clustered CPU architecture, most of this boot CPU is usually the little one. So all of these things happens in a boot CPU, in a single CPU, in a single thread fashion. And if you have machines with larger RAMs, like say few terabytes of GB and terabytes of memory, it's going to take much more time to boot up the system until user space is up. These are other functions as well that's kind of dependent on the size of the the RAM. So the bootmem init, this initializes something called the memmap data, or something called the page struct. So every page in the memory is being pointed by something called a page struct. So this bootmem init is responsible for doing memblock init and everything. It also is responsible for doing sparse mem init. So basically initializes all the sections in the RAM, and then populates the vmemmap data for the sections. And we have the init. It does a bunch of things like basically initialize all the memory allocators in the system, like stack depot, cache mem init, kmem leak initialization, vmalloc init, and then cache init. But the one that we are interested in is mem init, which the execution time depends on the size of the RAM. Basically, it gives all the pages that is free after the boot to the buddy allocator or the system allocator as part of the free list. So the execution time kind of depends on your size of the RAM. This is like a flow chart, visual representation. So you have this start kernel here, and as part of the setup arch, you have the memblock init, paging init, and then the bootmem init. And then outside the setup arch, you have the init. So all of these things, the execution time of these 4 blocks over here, they're all dependent on the size of the DDR that you have. So larger the DDR, more initialization work has to be done, more the time. So for here, for example, for a 12 GB DDR, in all of these 4 functions, we'll be doing memory initialization for the entire 12 GB RAM. And these are all done in a single-threaded fashion using the boot CPU. So the whole idea is, why not we do some of the initialization of the memory in a deferred fashion, like sometime later. So the general motivation is that we can reduce the boot up time by putting up the system with a very subset or a minimal amount of memory, just sufficient to initialize the kernel and initialize the user space. And then the rest of the memory can be initialized sometime later. Because when you're booting up the kernel, you don't need the entire 12 GB or X GB of memory to be present. So you can just initialize a subset of the memory during kernel boot, and then the rest of the memory can be initialized in a deferred fashion sometime later. So that's the whole idea here. And then once the kernel init is done, and once the SMP is up, like once you have the secondary CPUs up, we will parallelize initializing of the other remaining blocks in a parallel fashion. So this is actually originally inspired by something called a deferred struct page init. It's been there in the previous 5 kernel generations, but it's mainly for servers. Which has TBs of system RAM. So initialization of the remaining memory is done using k-threads. That's what the deferred struct page init does in a deferred fashion, and it uses something called like deferred probe mechanism, where once all the drivers are up, and then this feature kicks in, and then as part of the deferred probe, it initializes all the rest of the remaining memory. Possible impact is, since we are initializing at the end of the kernel, it might impact some of your other functions, which will be running at the end of the kernel. So there'll be a minimal performance impact. But what we observed is very minimum, that it's part of the noise. And this overall saves several milliseconds, depending on how much GB of memory you're trying to do in a deferred fashion. So that'll save you several milliseconds of your boot time. And I'll explain more about what are the KPI numbers for this. So this is a visual representation. So for example, if you have a 12 GB DDR, the first 2 to 3 GB, which is sufficient to initialize the kernel or to initialize the user space, I do it using the boot mem init. Basically, I say that, hey, kernel, you have only 2 GB or 3 GB, just initialize with this memory. And then the rest 9 or 10 GB, I do it in a deferred fashion. This can be done by k-threads, where the kernel takes care of the responsibility of doing the deferred initialization. Or you can use user space, where you have flexibility to add few memory to a different particular nodes and then zones, memory zones in the system. And also gives you the flexibility to add X amount of memory to this zone and X amount, Y amount of memory to other zones. So yeah, the general idea is boot up with just minimum RAM over here, and then the rest of the memory you add it later on. So from the device boots, kernel inits with this 2 GB, and then once the Android init, or basically your user space init is done, you use any user space entity to add the remaining memory in a deferred fashion. And that, of course, comes to the kernel. And then basically kernel is the one who basically uses the memory hot plug to hot plug in the remaining blocks. And I explain more about what memory hot plug and how we use memory hot plug to add memory to the system. This is also a visual representation here. So on the left side is the normal case, where you boot the system, for example, with a 12 GB RAM. You boot the system with the entire 12 GB. Everything is done in the boot CPU here. And this is the time. And I've also scaled the x-axis with the CPU horsepower, meaning how powerful the CPU is. So if you see here for the entire RAM, it's all done in a single CPU here in the left side. But if you see on the right side, when we do it using the deferred memory initialization fashion, we initialize only a subset of the memory, which is shown in the gray bar over here. And then once SMP init is done, once the kernel init is done, and once the SMP is up, then I have access to other CPUs and other bigger CPUs. And then I'll try to schedule initializing of this memory to different CPUs in a parallel fashion. So for example, your CPU1 and CPU2 will be initializing different memory zones, and they are all doing it in a parallel fashion. And then once, based on scheduler and everything, once I have CPU 3 available, and which is a much fatter or bigger CPU, that will be doing initialization for the other remaining memory, and then that will complete much faster than the left side, which is one single bar over here. So basically, you'll have a boot time saving of you'll have some significant memory savings compared to the whole single boot CPU mechanism over here. So adding memory to required zones. So the kernel kind of divides your system RAM into different memory zones. Something called normal zone, mobile zone, DMA zone. So the normal zone is the one that allocates memory for your DMA allocations, which are considered to be non-movable, where the pages are pinned over there. So you'll have a system where it might have a different spectrum of memory zones in the RAM. Like you'll have some normal zone for my DMA allocations, some mobile zone for like mobile applications, and then some DMA zone for DMA applications for the hardware that supports 32-bit DMA. So in order to do that, the kernel threads, they will not have knowledge about these configurations, like how much memory should be there for mobile zone and normal zone and etc. So instead of doing it in the kernel, we try to do it in the user space, which I explained before, where the user space will have knowledge about how much memory should be there in each of the zones, and it will try to use a memory hot plug to add memory to the required zone. This whole feature uses memory hot plug. It's basically like DIMMs for your laptops and PCs, where and if you want to add extra RAM, you just plug in the slot, and then the extra memory is been added to the system. So it's kind of hot plugged in. So we use memory hot plug to kind of initialize the remaining memory, and the user space can do something like echo address to the probe. So it can say that at this address add this particular memory, and the size of the memory is fixed. It's something called the block size. They are usually considered to be 128 megabytes for ARM64 systems. And then once you add that memory, you can do something called online movable or online kernel. So online movable means you initialize this memory block that just got added into the mobile zone, and then online kernel means you initialize this memory block that hot added into the normal zone. So in this way, user space can have flexibility to add memory to the required zones that's needed. And we use memory hot plug over here, and that's why we can prefer user space approach compared to the kernel approach. So limiting the boot memory, there should be a way to kind of limit the whole, for example, the 2 GB where I want the system to initialize just for the subset of memory sufficient to initialize the kernel and the user space. So there should be a way to let the kernel know that even if you have 12 GB of RAM, just initialize with just 2 GB or 3 GB of RAM. So we use something called as the mem equal to command line parameter. So what it does is, in the command line parameter, if you set mem equal to 2 GB, for example, it's going to boot up the system with just 2 GB, and then the kernel or the system will know that it only has 2 GB, even though it has physical 12 GB RAM. So now we have 2 GB, the kernel is initialized 2 GB. Now how do I know, or how does the kernel or the user space know what is the remaining end of the RAM? So in a 12 GB system, 2 GB is initialized, 10 GB is the remaining. So how do I know how much that 10 GB is? So in the DT, if you know, we have this node called memory node, which is usually initialized by the bootloader, depending on the DDR size that has been attached. So it will actually populate this reg property in the memory node, which will say what is the size, or basically it's a RAM partition table. It will say what is the size of the size of the partition, start address of the partition. So for simplicity over here, there's only one single entry in the reg which says at the 0 address, you have 12 GB of memory here. So in my kernel code or in my kernel driver, I use this, I scan this memory node and then get the reg property and then know what's the size of the RAM that is been attached. And then there's something called boot memblock address, which will say what is the end address that the kernel had booted up with, whether it's 2 GB. And I know that the boot RAM DRAM end address is 12 GB, so I know that difference is 10 GB now. And then this 10 GB has to be added in a deferred fashion. And the kernel can kick in K threads, or user space can do adding the memory of this 10 GB in a parallel fashion. So yeah, the rest of the memory can be initialized in async fashion, gives flexibility to add memory to the required zones and the required nodes. So we use mem equal to parameter to kind of limit the kernel boot, and then we add the remaining memory later on. So what are the ways to do deferred memory initialization here? One of them is the kernel driver method, which I explained before. So you limit the memory using the mem equal to parameter, and then you do use the memory hot plug function here called add memory driver managed. What this basically does is it adds memory using memory hot plug, but it's kind of driver managed. It's not a boot mem managed. So we use add memory driver managed with the particular size. So with this function, it will add this particular size using the memory hot plug. And we have this kernel, command line parameters here, to say what are the state. If I add this memory, so there's hot plug default state equal to online. What this means is if I add this memory, it will be initialized automatically. So you don't have the kernel doesn't have to do add pages or online pages by itself. So if you have this command line parameter, it will be initialized automatically. And then movable node, or something also called kernel node, this will specify what memory zone to be added by default. So if you have combination of these two, default state is equal to online and then movable node. So what this means is if I do add memory driver managed 128 MB, it will be initialized by default and it will be added to the mobile zone by default. So this way, I can add extra memory in a deferred fashion to a particular zone. But the limitation here is, we can only add memory to a required memory zone, and this cannot be changed runtime. So for example, in a deferred fashion, if you see over here, in this 10 GB, if I want to add 5 GB in the mobile zone, and then the rest 5 GB in the normal zone, that's not possible. You can only add this 10 GB in only required memory, either mobile zone or normal zone. So that flexibility is not there in using the kernel method. So to overcome this, we use the user space method, where still the kernel reads through the DT nodes, gets to know the mem equal to value, how much the memory has been, how much the kernel is initialized with, and how much is the remaining memory. And then those information has been fed into the user space via the sysfs nodes. Basically the mem block end of DRAM, and that's basically your 2 GB memory here. And the boot mem end of DRAM, that's the end of your 12 GB here. And then how much memory should be added to the kernel zone, and then how much memory added to the mobile zone, that is the kernel core and the mobile core. So this way, the user space will have flexibility to add required, the memory to the required zones, which was not there in the kernel zone, in the kernel method. But here, since we have to do it in the user space, we have to wait until the user space is done initializing. So there'll be a bit of a delay where your entire RAM has been initialized. So here's one example. So boot mem size equal to 2 GB, where if I have mem equal to 2 GB, so the system initializes it with 2 GB during boot. But my DRAM size is 12 GB, where I have a 12 GB DDR attached to the system. And then in one of these DT property, I have mobile core equal to 5 GB. Says, I need 5 GB of mobile zone. So the remaining memory is 12 minus 5, 12 minus 2 minus 5, which is 5. This will be considered to be put in the normal zone, which is the kernel core memory. So your RAM will be something like this, where the first 2 GB will be added by the boot during boot, and then the next 5 GB will be added by the user space using memory hot plug, and will be added to the kernel core. Basically, this 5 GB in the normal zone, and then the next 5 GB will be hot plugged into the mobile zone using the mobile core. So this way, we will have flexibility to add memory to different zones using memory hot plug. So boot time reduction, we have implemented this feature as part of a different mechanism in in SM8550 with 12 GB of RAM. And then with experimentations, we have seen that we get, by limiting with just 2 GB during boot, we see that we get about 160 to 200 milliseconds in the boot KPI savings. So this is roughly this boot KPI savings by adding 8 GB in a deferred fashion. So this is roughly like 20 to 30 millisecond of boot time reduction per GB. So if you have a system with much larger RAM, 12 or 16 or 24, you just boot up with 2 GB and the rest of the RAM can be initialized in different fashion, and then you will have a considerable amount of boot saving. So here 200 milliseconds is 1/5 of your second. According to our performance team, even if you have 1 millisecond of boot time savings, it's a plus. And we get this without any loss. Like there's no drawbacks. There's no performance impact, and there's no process or tasks that actually need your entire 12 GB during boot. So it kind of makes sense to just boot up the system sufficient to initialize kernel and the user space, and then the rest of the memory can be initialized in deferred fashion later on. So this is observed by profiling paging init and then the boot mem init. We do have some scripts that we run that captures the overall boot KPIs from the bootloader till the kernel init to the kernel modules init to the native daemons, and then till the user space init to the HAL init. So we do see that the kernel load and the kernel module load times, those are all reduced using this feature. But there's a bit of a catch there, which I'll explain. It's that the paging init, the boot mem init, and the mm init, these functions are the ones which will actually shrink if you initialize with the lesser RAM, lesser memory initially. But the catch here is these functions are done before the time init has been done. So basically, your kernel time will not be available before. Or your kernel time will not be available after your paging init, boot mem init, and mm init. So there's no way to or there's no way to rely on the kernel time to capture this boot KPI numbers. So we have to do something different. So we have to use some other hardware timestamps or clocks to kind of brute force a way of getting the counter values and then determine how much time it took from kernel start till till the end of the kernel init. So we had to use some of the hardware clocks or timestamps that we have in our hardware, and then that's because we couldn't rely on the kernel time because the kernel init is not available yet. So the challenges over here, it requires memory hot plug support to be enabled. So the memory hot plug support is present in ARM64. It's obviously there in x86 architecture as well. So it needs memory hot plug to be enabled. And so the full parallelism, though we say that we can initialize the rest of the RAM in a deferred fashion, it's not that mostly you achieve 100% parallelism. That's because of the zone lock. So what this means is, if you have, for example, 5 GB of memory to be added to the normal zone, you cannot split this 5 GB into 1 GB each, and then give it to a different CPUs in the different threads, and then try to achieve parallelism because of the zone lock. If you're trying to add memory to a particular zone, you'll actually take a zone lock. So other threads that are trying to add memory to the same zone, that will be waiting until the zone lock has been released. But if you're trying to add memory to a different zone and in a different node, that time you can achieve parallelism. For example, one of the CPU can add memory to the mobile zone. Another CPU can be adding memory to the normal zone, and then those two can happen in parallel. But you cannot achieve 100% parallelism because of the zone lock. So there's a bit of kind of leverage been taken out over here. So determining the initial size that you want to boot up the kernel with, that is sufficient to boot up your kernel or your user space. This is also a challenge. I've been saying 2 GB for your 12 GB RAM. We have seen that for more mature Android versions or for OEM versions, 2 GB is not sufficient. They usually require 4 GB or 5 GB to boot up Android. and then it's very hard to determine, for each generations of a chipset or system, it's hard to determine what is the fixed value for this. So there has to be some bit of a work to be done to budget the memory and to know how much memory is sufficient and how much memory we should limit during boot. And as I explained, like capturing the boot time is hard because the kernel time is not initialized yet after the paging init and then the boot moment and other ones. So we had to rely on other hardware counters that's available in the system to capture the boot KPI. So we have to have robust code and error handling. This is because we boot the system with limited memory, and then your deferred memory code or feature breaks, and there's no one to initialize the rest of the 10 GB memory. So your system is now stuck with 2 GB forever, and that's a big bummer. So we have to make sure that there's proper error handling done, where since kernel takes majority of the responsibility here, it checks if is the rest of the system is the rest of the memory being added to the system or not, it has been added by the user space or not. If not, then the kernel kind of takes over and then it adds the rest of the memory using whichever method it's available. So we have to make sure that the error handling or the code itself, the feature itself has to be robust, so that once you boot up a user space, whatever memory that's been there to the system has been initialized. And this might interfere with performance of the task that is running early during boot. But this, we did do some measurements, and we did not see any impacts in any of the tasks that are running once the user space is up. It might be, it's very small that it's hidden inside the noise in the standard deviation. So this feature isn't upstreamed yet. There has been a lot of discussion internally in our company or in our team about what is the exact savings that we have, and there's been a lot of discussions about is there actual parallelism been achieved, is there actual boot KPI been reduced. And then after a lot of conclusions and experiments, we did find that, and using the hardware counters, hardware timer and counters to do the measurements, we concluded that there is a bit of a savings because there will be some parallelism achieved if you're if you're adding memory in a deferred fashion later on. So we haven't upstreamed the feature yet, but right now we will be upstreaming it. We will be upstreaming it further. And then so we'll be using actually upstreaming the kernel method because if you upstream in this feature and then let the developers or the OEMs to implement their own user space method, then it becomes it's not an end-to-end solution, and then we have to rely on the how the developers would implement the user space. So we'll actually upstream the kernel method by fixing the limitation that I mentioned, where the kernel will have way to add memory to a particular zone. So something like add memory zone, which is not present, but we'll be thinking of sending it as an RFC to the community, where the kernel can add memory to a required zone, and the kernel will have the flexibility that the user space has actually. So this has its own limitations, where you have to make sure that the zones are not discontinuous. For example, you have 3 GB of normal zone, and then you have 2 GB of mobile zone, and then you cannot have another normal zone. So it has to be fixed. First 6 GB or X GB has to be normal zone, and then the rest have to be mobile zone. So you cannot have mixed memory zones in the system. So those things we have to make sure that such calls are not honored, and we have to put all those checks and limitations in this whatever API that we're going to implement. So it has its own limitations, and it might and let's see what the upstream community has to comment on this. But yeah, so it'll be implemented as kernel driver, where a combination of these 3 command line parameters, the mem equal to 1 used to limit the memory during boot, and then the deferred mem kernel core as part of the percentage, because you cannot put numbers over here like 5 GB or X GB, because you don't know what DDR, what's the size of the RAM that will be attached to the system. So we'll put something like percentage-wise. So for example, for 12 GB DDR, we'll have mem equal to 2 GB to limit the memory during boot. And then the mobile core is equal to 40%. So what this means is 40% of your 12 GB will be for, of course, rounded off to, the mem block size or 1 GB here. So 40% of 12 GB will be added to the mobile zone, which is 5, and then the rest of the memory will be added, which is 5 GB again, will be added to the normal zone here. So this way, without relying on any user space implementation, we'll have like a separate kernel driver. And this can be, of course, enable or disable using maybe a config or maybe a command line parameter again, where if you have enabled it and if you have all these 3 parameters, you'll be able to achieve some boot time savings by initializing some part of the memory in a deferred fashion. So I'll keep the next few minutes for questions. How do you want this?
Thank you very much for your talk. I have 2 questions. I'm wondering if this can somehow help to reduce power consumption by maybe it needs to interact with the DRAM controller, but until the point we may actually want to have more memory, maybe we could turn off some DRAM modules and could get the reduced power consumption. And my second question is, so you mentioned that there might be some performance impact for the applications, but I wonder that if the current implementation already extends the maybe page fault path body allocator, so that when the application requires a huge amount of memory, when the physical memory is still not initialized, I assume that my Linux kernel would perform killer and start getting killing the processes. But it's not performance impact. I think it's much worse than performance impact. So I wonder how you actually handle when the user space tries to allocate more memory when the enough amount of memory is not available.
Okay. Yeah. So for the first point about the way of turning off some memory for initially for power consumption, is that the question, right? So yeah, we did implement that feature. It's something called as PASR, partial array self-refresh. And then I myself did present this in the LPC last year, where for example, you have this 12 GB RAM over here. You won't need the entire 12 GB RAM, for lightweight usage of the system. So in that way, you can turn off, let's say, 5 GB of RAM during lightweight usage of the system, and you can use this technology called PASR, partial array self-refresh, to turn off the memory, turn off the self-refresh currents, and then save power. So we do have implemented that, and I've presented this as in LPC last year. But another note to the power savings or the power consumption is that during deferred memory initialization, we do try to use the bigger CPUs, which will consume more power. And according to our performance team or power team, we don't care about power consumption during boot. As long as we can boot the system much faster by taking more power, we will of course try to gauge that and then go with more performance number rather than power. But yeah, we do initialize it. So the kernel driver does add memory assigned to the higher horsepower CPUs, and we don't care about the power. And for the second one, in the user space side, we will try to make sure that the memory is initialized much before your actual processes are being initialized. So this is much before, I would say, the very early part of the user space init, maybe sometime HAL, before you let other third-party applications to run, so that you don't kick into OEM killer or killer or the LMKD in the Android. So this is way early in the user space init, where we initialize the memory, and then, so if you see here the HAL init, HAL client init. So as part of the Android core and then HAL init, we will initialize it. We will initialize all the memory in this, in this phase, and then once this completed, all the memory is initialized, and then all the other HAL clients will be initialized. So this will make sure that we will add all the memory much before your other user space applications have been run.
Thank you very much.
Yep.
So maybe I'm exposing my ignorance, but the tuning stuff seems difficult and scary to me. And
Okay.
So like anytime I have to come up with knobs and sorry.
The tuning stuff seems difficult and scary, and maybe I'm ignorant, but anytime I see knobs, I don't want to have to come up with knobs and maintain those across kernel versions and boards and stuff. I kind of want it so that I can turn on a flag that says, make it boot faster, but just boot as if this flag wasn't there, right? So like the percentage between movable and normal and DMA memory, it should just, without me telling it, it should just do the same thing as it would as if I booted without this flag, but just boot faster. And so, like, in order to feel like I could use this and maintain it, that's what I really want.
Yeah, I mean, I totally agree. I mean, this whole part of tuning and everything, it's a time cumbersome thing, and it's scary as well. And every time we have a new chipset or a new system, we have to do this memory budgeting, do this whole math, and then do the percentage wise. It would be cleaner if the kernel somehow gets to know this automatically and then figures out how much memory is needed for the boot and how much memory can be initialized later on. And if there's a mechanism where the kernel can do it, kernel can determine it by itself, where the user doesn't have to depend on, rely, or doesn't even have to know the knowledge of all these things. Just by enabling a flag, the kernel will decide by itself how much memory should be for boot in it and how much memory should be for deferred in it, and the kernel should do it by itself. That would be great.
Couldn't it like register fault handlers, and if it notices that someone tries to access too much, it starts initializing then or something?
So something like demand paging. Yeah, that's one idea that it can be implemented. But yeah, I mean, this, we have been doing it manually or at least it's part of a different feature actually. So to say, we're not doing all this, percentage wise, but we do set aside like mobile zone, especially for this memory offlining feature, the power saving feature that was mentioned. But yeah, we are working on this, and once we have a solution, or maybe we can ask the community for comments as well, where we can have this feature enabled, and the admin or the user doesn't have to worry about all this tuning and stuff, and the kernel can do it by itself. Something like demand paging. Yep. All right. Thank you.
Initialization, even after
Hello.
There you go.
we're usually doing is allowing that for Q&A if you want. And if you don't have
Hello. Let's say that's working. I'm just going to wait for the guy to say it's time to go. I don't know, is he recording yet? So, I don't know, is he recording? I'll go find out. Where's that go to? Oh, there he is. Should I wait for you or should I just start? Okay, pardon me. Just start, he said. Just start. Sound. Cool. Okay, so welcome to my talk on implementing a solution for MIPI cameras in libcamera. So, first of all, introductions. Hans is not here, but I gave a version of this talk with Hans at FOSDEM earlier on this year. So all of these slides come from FOSDEM. I updated the logo though, just for you guys. So Linaro and Red Hat and libcamera. Libcamera is both a project and an organization. It's a company. Have been collaborating together to solve a particular problem with MIPI cameras specifically over the last while. So this is me. I'm Brian. I work on the Linaro Qualcomm landing team. I recently inherited, not about a year ago, I suppose, the camera subsystem in the upstream for Linux. Yeah, you can find me on IRC sometimes. There's my Code Linaro, the place I dump all of my in-progress kernel work. There's my GitHub, and don't look up my handle on Twitter unless you want to discuss politics. Which has nothing to do with this presentation, by the way. So, what does this talk about? A, Bayer encoding. What is Bayer encoding, and why do we care? What is a hard ISP? What are the 3 A's? What is an ISP? Soft ISP and libcamera. Why is that a thing? Why do we care again? Libcamera and pipewire integration. The future plans for what we want to do with soft ISP and libcamera, and a demo. Always very risky. Always very risky doing a demo. Okay, so what is Bayer encoding and why do we care? I freely admit, when I inherited the CAMSS stuff, I didn't know the answer to that. I'd heard of Bayer, but I didn't really know. The question is, what is it and why do we even use it? And so, like, I found some interesting terms when I was researching why Bayer encoding was created to begin with. And the main reason why is that your eye is sensitive to this bit of the spectrum right here. this kind of greeny yellow, Jesus, that's right in my eye. This greeny yellow, I'm quite sensitive to white light as the projector myself. This greeny kind of yellow bit of the spectrum here. So your eye has rods and cones, as we all know. So when you go from light into dark or dark into light, it literally takes a while for you physiologically to switch from one mode to the other. Rods are scotopic and cones are photopic. I suppose it's not very interesting to go into the terms of it, but then the question is, how do we encode that? So our sensors are actually, if you think about it, they're just ADCs in a sense that react to light, and they have no real concept of spectrum, and they don't care how we see the spectrum. So what we do is we put a filter over each one of the individual sensors that's sensitive to a particular component of the frequency spectrum. And since we've established that you're more sensitive to green than to blue or to red, it kind of makes sense that we want to encode more spectral information in the green bit of the photons hitting the sensor. And so this guy called Bruce Baer in 1974 came up with the scheme to encode the maximum amount of retrievable information. Because we need to get red, green, and blue. We want to retrieve more green than anything else. And so the Baer encoding pattern is literally something along the lines of green, blue, green, blue, green, blue, green, blue, red, green, red, green, red, green. There's his paper. I thought this was kind of very analog. He just wrote it down on a little bit of paper back in 1974. So there are a number of ways of, once we've encoded, Bayer encoded information to retrieve it, right? So we now have, a lossy encoding format, and we need to retrieve the maximum amount of data from that format that we can when we are reconstructing, because what we want is red, green, blue, red, green, blue, red, green, blue, red, green, blue, but what we get is green or blue or green or blue or red, which is going to be one line lower. So it's kind of an interesting approach, and there are a number of different ways of retrieving that information or inferring the information based on the component of the adjacent encoded pixels. So if you imagine that at the red here, you're still going to have information that pertains to the green beside it, and vice versa. And so therefore, there are a number of algorithms to infer, make a fairly good guess as to what the green or the blue was for any red, and so on. So there's label, nearest, bilinear, and Mallar-Hay-Cutler. I'm terrible at pronouncing non-Irish names, never mind. Non-English names. But typically, this one here is extreme. And as the quality of the retrieval goes up, the computational time and effort also goes up. I mean, it's the same principle from any scheme and anywhere in computer science. Typically, you will find that nearest or bilinear retrieval is used because they're pretty close, they get you pretty good results, and they aren't as computationally costly as the last one here. So here is what it actually looks like when you take. So this is from a really good paper by a guy called Morgan Maguire. I have an apostrophe here. I don't think that's correct. I think it's Morgan Maguire, not Maguire and Morgan. When you look at a Bayer encoded image, it looks a little bit like this. So there's a mosaic pattern. It looks like a mosaic pattern, something you'd find in the Roman Forum. We'll call this ground truth, raw image label. You see, you don't want to be getting label out of your camera when you take a picture. Nearest, you may or may not be able to see, it's quite edgy. Bilinear is pretty good. And as I say, the other one here, which is much more computationally costly, is far better. With the high resolution sensors we have now, the last debayering method kind of doesn't make sense because we have loads of information to work with already, and so typically again, it's nearest or bilinear. Okay, so what is a hard ISP? So if you think about it, every time you take a picture with your phone, a whole bunch of stuff is happening. It's not just debayering the image, it's doing a lot more than that. It's correcting for exposure, it's maybe doing autofocus, auto white balance, correcting lens flare, and usually that is done in a hard, so for your phone, that's always done in a thing called a hard ISP. So basically this works on the principle, again, of locality. You've received a frame into your DRAM or maybe SRAM somewhere, and you need to process it before you hand it off to user space for stuff. And that process is typically called a hard ISP. So that would be a concatenation of hardware silicon blocks and firmware that process that incoming data. The first part of that is just to debayer it. So interestingly, well, for me, if this here is ground truth, i.e. the image that you want to take, the one on the left is underexposed and the one on the right is overexposed. Now when I did this at FOSDEM, the one on the extreme right looked better to me, and I thought, God, you know, the one in the middle doesn't really look like what I would call ground truth. But it's interesting on this projector, it's different. Camera companies, including Apple, Google, Qualcomm, who I work with extensively, any Panasonic, Sony, whoever, they consider the method for debayering, well, not really. I mean, everybody knows debayering we've been doing since 1974. It's not secret sauce by any means. But hard ISPs are treated as a kind of holy grail that thou shalt not touch or interfere with, and must be locked down with every legal mechanism available. And the truth is that for some of the more advanced algorithms, this is certainly true, but for the boilerplate stuff, it's really not. So the 3As, autofocus, auto white balance, auto gain, I'll get back to these a little bit later. This is kind of standard stuff. And if you just want to use your MIPI camera to take pictures of, you know, birds in the back garden, you want to debayer, apply these 3 fairly simple conversions and just dump the data out, right? More advanced stuff, sensor tunings. I mean, I say joking, but not joking. You know, setting the gain on the sensor is not really proprietary information. It's not secret in any way. It's just a value on an analog input. But again, the companies are very sensitive about disclosing this information. Skin tones, low light, noise reduction, contrast, lens flare, and these are all considered, you know, secret sauce. And my personal favorite is the Black Mirror reverse. I don't know, maybe we'd make a Star Trek joke about that. But I mean, take a look at the picture and remind yourself that this is one picture that was taken. So somebody pointed the camera at a lady in a shop and took one picture, and the outcome was this. I'm going to point out the obvious. Those are her hands. And this is why this is a very freaky picture. Is it a bug or a feature? I'll let you decide for yourself. But I think maybe you call that a bug. They took 3 pictures and they stitched it together. And the software thought it was 3 different people instead of 1. But this is the kind of proprietary information we need to protect. Ha. So soft ISP, what's the problem that we're trying to solve? The problem that we're trying to solve is on a number of different SOCs, what we get out of the
the kernel interface is just Bayer encoded data. So we will just take the data straight out of the sensor, dump it into user space, and not enable any of the hardware acceleration to de-Bayer, to apply the 3As, to tune the output at all. Like I say, there's a reluctance to disclose stuff that's considered secret sauce. Sometimes it goes in the other direction. It's acknowledged that we can disclose a lot of this stuff, that it's not really secret sauce, but the subset that we're going to disclose won't produce a good enough image, which personally I can't get my head around. So examples of where we need to use a soft ISP, IPU6 for the Intel, CAMSX for Qualcomm SOCs, the BeagleBone Play is another example. I think all of that class of TI SOC requires, not all actually. There's a BeagleBone Play, and then there's another BeagleBone that's on their website, and one has an ISP and the other doesn't. And what we want really, I mean, so I've been going on about vendor-specific solutions, and that's nice. But for an open source solution, what we really want is a reusable solution, something that we can repeat and obtain pretty much the same results across SOCs. That's the right thing to do from an open source and a sharing point of view, and that's where we want to get to. So when I came on to CAMSS, it was at the same time that we were starting to produce some of these laptops with Qualcomm SOCs inside of them that have MIPI cameras. And people start saying, well, where's the camera? Why doesn't the camera work? And at the same time, nobody wants to disclose the hard ISP. Plus, it's a lot of work, right? It's going to take 6, 8, 12 months to get from just dumping raw MIPI data into user space to a real solution that can be upstreamed. So we started looking into libcamera and doing the processing in there. And as a first pass, we said, well, we do it in the CPU, and then maybe we will start to enable some of the DSPs in there, and then maybe we'll start to use the GPU as well. And so we were working away on that, and at pretty much, and you see this a lot in open source, I think, at exactly the same time, a MIPI camera was being produced for IPU6, and the Intel platform was in the same situation, and Red Hat came along, and we synced up with them, and we started collaborating to produce the final solution, which is about at version 8 now, if you look on the libcamera mailing list. So we're kind of, saying, please put a full stop at the end of that comment. And the libcamera people have been very nice. They've been turning up to meetings regularly, giving us design. So in Paris, which I didn't attend because I had COVID, but I did attend virtually, we came up with this design. When I say we came up with this design, the libcamera guys said, please do your software exactly like this. So this is the basic design. There's a class that does the ISP bit, and then another class that does the IPA bit. The IPA bit is the thing that calculates the sensor, what am I doing? I'm doing statistics. Statistics come out of the ISP, and the sensor tunings come out of the IPA. So that's the basic design they want. And that's what we did. So Hans de Gold, and he's very well known. Everybody knows who he is. Came in at about version 2 of the patches. We're now on version 8. And my colleague, Andre, I can't say, who can say that second name for me? I just call him Andre. My colleague, Andre, did most of the work to get it up and going on the CPU. So most of the design work, the first pass at the debayering, the first pass of the 3As, the sensor tuning. I've just kind of been playing along there, helping them test, participating in the meetings and so on. Oh, no, don't go to sleep. Okay, so that's nice. libcamera produces a debayered image and applies some level of 3A to it, plus tuning. Does that just work? Unfortunately, no. It doesn't just work that way, because on Linux, what you usually have is a thing called a UVC camera. That's a USB camera that you plug in, and the libraries know how to talk to that. Hangouts knows how to talk to that. Zoom knows how to talk to that, and off you go. Most of the browsers don't know how to talk to a video for Linux camera, so you're kind of stuffed. And in any case, libcamera is producing frame buffers that need to be consumed. So coming to the rescue is Pipewire. So actually, Jan Grulich in Red Hat did all of the work to get libcamera and Pipewire talking to each other prior to us even starting this project for libcamera. This is actually Hans's slide, so I'm not really across the detail of it. Hans has made a copper repo for Fedora Rawhide. I think that's what it's called, Rawhide. I did something for the Linaro Debian distro that I'm running here. And Firefox has a Pipewire config option that you can switch, which will allow you to consume it allows you to consume frame buffer data out of Pipewire. So Firefox doesn't know where the frame buffer data is coming from. And in this case, what we're doing is getting libcamera to feed the data into Pipewire. So that it can do the discovery mechanism through Pipewire, as well as the consumption of frame buffer data. So that actually is a operating system level complete solution for your Hangouts. And I have run a Zoom call, not Hangouts, that way. Unfortunately, Chrome the Pipewire integration is for some reason been stuck in there for the last 18 months. Whoever owns the merge button hasn't hit merge, and I think it's suffering from bitrot at this stage. I'm not even sure if it would merge, so that needs to be addressed. We need to get in there and figure out why nobody wants to hit merge on Chrome. So future plans. Unsurprisingly, and if I have the time, I'll pull up a terminal and show you. The CPU solution also implies high CPU consumption, believe it or not. So on an IMX8, one of my another colleague of mine, well, he's a co-worker, I suppose colleague is the right word. Anyway, Milan, who works in Red Hat, was running this on an IMX8 for I think a 4K sensor, and was getting 2 frames a second. So yeah, that's obviously, no bueno. That's not useful. On the Qualcomm laptop, I can get 30 frames a second easily. Hans gets 30 frames a second easily, but these are quite powerful processors in comparison to, some of the, in the embedded space. So yes, this is a solution for your IPU6 if you're not too concerned about battery and you're doing a 10-minute call, it's fine. But you couldn't really put it on a pole top and run your IMX6 from it, for the simple reason that we're debayering with the CPU. So what do you do about that? So I was kind of very wet behind the ears when I started looking at this. So I started saying, OpenCL, everything works in OpenCL, it's great. It's doing OpenCL. And I was gently educated by the, well, first of all, OpenCL, it has Qualcomm support, but it has downstream Qualcomm support. So we would have to go and we would have to go and implement an upstream solution for OpenCL to offload into the DSP or the GPU. So personally, I think that's a project worthwhile doing, but that's an order of magnitude higher than just getting it to work on the GPU. So what we're looking at there is, it says fragment shaders here. I did look at fragment shaders. The issue with using okay, sorry, pardon me, let me take a step back. You can use a GPU to debayer, and it's almost a perfect mechanism to do it because it has lots of little cores that operate in parallel, right? So if you think about it, every single one of those pixels will then be delegated out to a core at the end of the day if you do your algorithm right, and it'll all just go in parallel. It'll do, a few cache lines, and it'll be done. It'll be done. So I say cache lines. The libcamera solution requires an uncached buffer to come out of the and to be passed out as a frame buffer. And you're going to ask the question, why is it uncached? And the reason why it's uncached is because some of the video encoders, like Hantro and IMX8, need physically contiguous memory and uncached memory at that to work. So if we had a generic solution in libcamera that used cache buffers, we would be precluding something like the Hantro. And so therefore, on the Qualcomm, on the Intel machine, we have to use uncached buffers, and so we're debayering inside of an uncached buffer. And now you're seeing why this is so computationally costly for us, because it's uncached. And so therefore, GPU acceleration is where we want to go, because we can put a buffer into the GPU, have it operate on that. We can have it copy it over and do a cached computation and give us a buffer out. We can copy that back into an uncached buffer. There are many different ways we could have it operate on an uncached buffer massively in parallel. So a scalar processor is not really suited to an algorithm that's done pixel for pixel, whereas superscalar is maybe the wrong word. Highly parallel system like a GPU is. Upstream in libcamera, we already had a GPU, an OpenGL fragment shader to do debayering. So the first idea I had was, okay, let's just reuse that, because good software, you don't throw it away, you just reuse it. Even bad software, don't throw it away and just reuse it. Don't make any effort you don't have to make. But reading the pixel data out of a GPU when you have debayered it is extremely slow. You end up going through a thing called GL read pixels, which does the pixel conversion to RGBA, no matter what the internal format was. So that is horrifically slow and cannot be used. And I spent a while kind of fighting with the buffers. So could I get a DMA buffer, and could I pass it into the GPU, and could I use this fragment shader again? And eventually, I think we decided that a compute shader was the way to go. So what we're looking at here is a multi-pass compute shader to kind of semi-solve this problem generically in libcamera. In OpenGL, why in OpenGL? In GLES specifically, because it's the lowest common denominator across embedded platforms. So yes, Vulkan is the way to go, but not every one of these low-end systems is going to support Vulkan. And everything that supports Vulkan can support OpenGLES via Zinc. So that's the theory, and that's still a work in progress. So you can see here, actually, Hans has kind of laid out contrast enhancement is going to go into the CPU, but you can see all this other stuff here cannot be done in CPU. It's just, it's never going to work, so we have to go to GPU to make this work. libcamera will go to version 0.3 when CPU ISP is merged. At the moment, it's at 0.2, and that's the kind of big thing we're waiting for to get done there. Here are all my references, and hopefully, oh, there I am. Hello. There it is in progress. Give yourselves a round of applause, lads. Great stuff. Questions? Oh, let me get a mic for you. Hey.
Yeah, great presentation.
Thank you.
What all stages of the ISP were developed in the soft ISP? I didn't catch it from the diagram.
Can you answer that question
What
again, sorry?
stages of the ISP were have been implemented so far?
What stages of the soft ISP have been implemented?
Yeah.
No problem. So, this. We have debayering and the 3 A's.
Okay, debayering and the statistics. You're saying. Okay,
Yeah,
right,
so
yeah. Okay.
we're accumulating statistics, we're pushing the gain up and down. We're doing, the 3 A's at the
And
moment.
statistics for all the 3 algorithms.
Yes.
Okay.
Yes.
Cool. How much of percentage of CPU does it consume to run it on the top? Yeah.
Oh,
that,
that's okay. I can follow it. Yeah, let's find out. Let's open the terminal and find out. It varies, right? So actually, you'll see here, I'm getting about 14 frames a second because I am running a debug build there. But trust me, if I run, the release build, it goes up to 30. So you'll see there QCAM is using 110% on the debug build of one core, a 1.5 gigahertz core. Yeah. So a lot. That will come down to about 60, maybe 80 when we're running the release build. But when you go down to an IMX8, that's 5 or 6 years old, and this is a 5 megapixel sensor. So if you go down in computational power and up in sensor resolution, eventually you run into a wall. But I mean, interestingly, the paper from this guy here, from Morgan Maguire, is from 2009. Yeah. And oh dear. And he gets really great performance from a 2009 era NVIDIA. So, that's nearly 20 years ago now. I'm going to say that we have high hopes that on an IMX8, maybe even on a single core IMX7, the GPU should be able to do a fair amount of chunking through once we get it going. Compute shaders. And the interesting thing about the compute shader actually is I think, and I'd be happy to be corrected, I think that the syntax is transferable from GLES to Vulkan. So if you do it for GLES, you can still conceivably run the compute shader on Vulkan. So that's nice. So, if for whatever reason you can't run Zinc, or somebody wants to come along and write a Vulkan layer into libcamera, you don't have to go and rewrite the debayering and the 3As and whatever other algorithms we put in there, and it's repeatable, right? So it's still repeatable. That's what I really like about moving it out of the SOC and moving it into the GPU in an open source project, is it's repeatable, and yeah, that's why I'm excited about it. More questions? Oh. You're loud, but I need to get you on the. You're not so loud that they'll hear you over the video.
That's a challenge.
It is.
So completely new to this.
Yeah.
So naive question. So the 3As, I'm guessing, are not about fixing the pixels you have.
No.
It's about getting the next frame adjusted so that
Correct.
they're better. Is that right?
3As. I didn't go through that. Auto white balance. So, here is an image with, I wrote it down. Yeah, the white balance is wrong in this picture. That's why it looks blue.
But it's not trying to fix the pixels in this frame. It's trying to measure this frame and set the sensor up for the next frame to be better. Is that correct?
It provides, so you accumulate statistics when you are debayering the information, and then you provide parameters back to the next iteration of the debayering of the frame, in which case you are going to correct the white balance. Okay. So some of it is sensor gain, but some of it is also color weighting.
Okay.
So
but it's about fixing the next frames.
The next frame, yeah, because
and the autofocus is a signal processing thing or a mechanical thing?
Well, it's like when you touch. Well, the superficial example, when you touch your screen, it focuses. It doesn't. There's no optical zoom there. It's digital focus. More questions? Yes. Gentleman in the green.
I was just going to say, did you look at any sort of the vector processing type instructions like Neon for improving the algorithms?
So Neon. So yeah. So the CPU algorithm has been tweaked to do bilinear, and kind of it's more nearest neighbor at this point. We are not breaking out specifically into inline ASM. We're just leaving it up to the compiler to decide whether or not it's going to go and do something using a vector instruction like Neon, or any of the SIMD instructions in x86. So, yeah, we trust the compiler, which is, maybe now is the time to try and, premature optimization is some kind of, deadly sin in software. So maybe now is the time to go and do that optimization on the CPU side. Personally, I'm more interested in optimizing in the GPU, because I think that's where we're going to get the bang for the buck in the end. But yes, it was looked at, but it wasn't inlined specifically. More? Going once, going twice, going 3 times? No? Cool. Okay, thanks very much for turning up. I don't know how I'm supposed to end the presentation. I guess everybody just leaves. Yeah, okay. I'll give myself a round of applause. Awesome. Okay. Who's next? Hey.
I actually tried your
testing? Okay. So we'll get started in about 5 minutes.
Recommend removing your badge.
Okay, yeah, makes sense. Okay, I presume I'm on. We'll get started. First, I gotta wake up the laptop. All right, so let's get started. We're talking about AMP VirtIO. So I'll explain what these things are as we go along. First, a little bit about me. So I'm Bill Mills. I've been with Linaro for about 3.5 years. Been a member of the OpenAMP project for about 7 years, and founding member of the Yocto project. Focused exclusively on open source since 2008, and long history before that. A little bit about Linaro. I like to think of Linaro as the nexus of open source for ARM. Linaro has a lot of missions. One of them right now is VirtIO for the edge, and AMP VirtIO fits into that. A little bit about the OpenAMP project. The goal of the OpenAMP project is to make the user's job easier, the programmer's, developer's job easier whenever you're dealing with an AMP system, which is, it could be two OSs, different OSs talking to each other, different CPU cores, or different discrete systems, even if those things are the same. So we'll talk about that a little bit more. So the outline of today's talk, so this is in the ELC track, but this touches on Zephyr, it touches on real time, it touches on safety aspects. So it really kind of fits into all the tracks that we're talking about this week. I'm going to talk about the background of what we're doing and why we're doing it, a review of what VirtIO MMIO is, and then the problems that VirtIO MMIO has when trying to do this on an AMP system, and solutions, our suggested solution to those problems. Talk about the status and the code pointers, credits, and then at the end I'm going to talk about a probable change in direction that we're thinking about. And then we have the wrap up. So why are we talking about VirtIO? So I think of VirtIO as the universal donor for paravirtual device interfaces. VirtIO grew up in the KVM ecosystem, but it's being developed by it's being implemented by other hypervisors. It's being used by bootloaders, aftermarket software, lots of different things. So again, kind of the universal donor for virtual interfaces, virtual device interfaces. AMP VirtIO, why are we doing, so all those good things about VirtIO, we want to bring them to AMP systems. So different cores, different systems, different operating systems. Things that make VirtIO traditionally hard to implement between those systems, we want to overcome those and provide VirtIO in that context. And then for our definition, the lowest common denominator to make this work is a shared memory and some sort of bidirectional notification. We'll talk about different instances of that. So why am I talking about Zen and Zephyr? Well, both projects are good open source projects with open governance. Both are have a group that's looking at functional safety, which is important. So if you're going to have a reference hypervisor, Zen is a great one to choose. If you're going to have a reference RTOS, Zephyr is a great one to choose. Did I say that right? Zen, hypervisor, Zephyr, RTOS. So they're great references. The OpenAMP project wants to be neutral. Linaro wants to get VirtIO everywhere, regardless of hypervisor. OpenAMP wants to be portable to lots of different RTOSs, but these are the leading integration reference platforms. Zen is a type 1 hypervisor. Type 1 hypervisor is very important when you're dealing with functional safety or mixed critical systems. being able to update the kernel without updating the hypervisor, being able to safety certify the hypervisor to a higher safety level than you can for the Linux kernel. These are all important things, and that's why we're focused on a type 1 hypervisor. So here's an example of an AMP system. This is sort of the classic example where OpenAMP has always existed and been used. But this is an AMP SoC. AMD Xilinx makes these, TI makes these, ST makes these, NXP. You got lots of examples here. But you have, traditionally, you're going to have some SMP capable cores that can run SMP Linux, and you're going to have some other types of cores. They could be Cortex-M or R or DSPs or some other type of DSP that's not going to be running Linux. So, and this is what OpenAMP has traditionally done. To make this work, there's normally some sort of shared memory, usually firewalled or protected, so the MCU can't trash Linux and things like that, and then some sort of a mailbox system. Again, this is where OpenAMP has always existed, but now, even in this situation, we're not going to just do RP message, we're going to do other types of VirtIO. So we also want to expand out to AMP systems that are created using PCIe. So you have a root complex, maybe it's an x86 machine, and you plug in an ARM SoC-based PCI card. You've created an AMP system. Those two systems will not share a hypervisor. They can't use traditional VirtIO in this case. Even if both sides were ARM or both sides were x86 and they were both running Linux, it's still AMP because it's not the same Linux instance. So we have this case with the root complex and endpoint. Another common situation that you find, I see it in automotive references more and more, is where you have two PCI systems. They both think they're root complex, but then they're plugged into what's called a non-transparent bridge. So that transparent bridge bridges those two systems, but each side of it thinks they're the root complex. And that non-transparent bridge will allow you to share some portion of your memory with the other side, provide some sort of a doorbell mechanism. So again, that's all we need to make this work. If you talk about the chiplet ecosystem, I don't know much about the chiplet ecosystem, but it looks like this is going to be a good match for that ecosystem too. It's PCIe that's being used there, so I think this fits right in. And with that ecosystem, you're kind of mix and matching. You can easily create different types of AMP systems, so I think this is going to be important. To simulate this, what we do is use two instances of QEMU, and QEMU supports a peripheral called IV shared memory that appears like a PCI card to the two instances, but then it has a shared memory between them and doorbell mechanisms, and those doorbells end up as MSIs on the other side. So with those two QEMU instances, you can simulate right on your desktop this kind of a system. Okay, so the other type of AMP that we're talking about is an AMP that's created under a hypervisor. So if in this instance, they're all A53s. You could run SMP on all of them, but you've chosen to partition out some of them, and you're going to run an RTOS on those, and you're probably going to pin those virtual CPU to physical CPU. You're going to worry about real time on those. Maybe you're interested in functional safety for those. And then you're going to have other CPUs where you're going to let Zen, overcommit and float the virtual CPUs. And so that, again, that's sort of a mixed critical system. This is AMP because you have Linux plus RTOS. So it's still AMP. And we're going to talk about, well, I guess that's the next slide. So why do you need us to do in this case? But then you get into a mutual trust. And so if either side screws up, then you screw up both sides, yeah. So yeah, so the statement from the audience was you don't really need the hypervisor. You could just set things up on both sides to do this. But if you do that, both sides sort of have to trust the other not to screw up. The hypervisor is there. If you have the hypervisor present, he can isolate you from the other side screwing up. So Zen has their own paravirtual device drivers. Zen has been adding support for VirtIO already, and this is the traditional VirtIO. So why do they need VirtIO AMP? Well, at least right now, the way Zen does VirtIO is, we're going to talk about the magic memory in a minute, but whenever you do a transport operation, the guest writes to the MMIO area, the hypervisor traps that, turns it into a message called an IO request, and sends it over to DOM-U or whoever's serving that virtual device. That virtual CPU is now stuck and can't make progress until the other side responds to that IO request. So if you're trying to do real time or you're trying to do functional safety, you've now got a big problem because you don't know if that other side's going to respond. You don't know, it could be a big code base that's hard to safety certify. So you want to decouple these things. So if you use the AMP techniques, that then it comes into, you get your shared memory the way you want it, you send a notification, now you go about your business, the device side will respond or not, and you have to be prepared for the or not case, but you can make progress on your side regardless of what he's doing. So that's why we think the AMP techniques are, would be a benefit to Zen. So let's talk about the AMP part. First off, a review of what VirtIO MMIO is. First off, if you don't know VirtIO at all, there's the protocols or the device types as they're called in the spec, that, VirtIO block, VirtIO net, console, RNG net, I2C. So these describe the wire protocols for the contents of the buffers. You put that data into buffers. You put those buffers into V-rings. The interface is called VirtQs, but the implementation is V-rings. And then you notify the other side through the transport mechanism. Before you can do any of all that, the transport mechanism has to negotiate, this is what type of device you're dealing with. The driver side tells the device where it put the V-rings and how big they are, and what features you're going to have negotiated for this. And in VirtIO 1.2, there's these new things called shared memory segments. All that gets negotiated through the transport mechanism. And there's multiple transport mechanisms. VirtIO MMIO is one. VirtIO PCI is another. At the end, we'll talk about VirtIO CCW, which is an IBM thing. But if you look at VirtIO MMIO, which might be the easiest to understand, and typically the one we want to implement in an RTOS, it consists of two things. A 256-byte area, that's the MMR area, and then typically a 256-byte area for the config structure. So the MMR space has the magic numbers, the version, the device types, and it has configuration for the VirtQs, the features, and things like that. The 256-byte config space is normally information provided by the device to the driver about the device. Usually it's fairly static, but the spec allows for a very interactive config space The device could be changing it. The driver could be making changes. There can be side effects to changing the config space. Most people rightly don't make use of those features, but it is part of the spec. And all that VirtIO, MMIO stuff uses this hypervisor magic that I talked about. Like the notifications, you send a notification by writing to something, and that's supposed to automatically clear. Receiving a notification, an event, you read the register, it's supposed to automatically clear. If you're just dealing with plain memory, that doesn't happen, right? So we need to eliminate that magic. So the AMP VirtIO, at least the definition that we're talking about today, is a variation of VirtIO, MMIO, with several changes. So we're talking about a device side, a driver side, and then I defined a role called a coordinator. A coordinator can be something very simple, like a bootloader that zeroes out memory before things start, or it can be an active component on in one of the domains where it is doing hot plug of devices, and it can be very active. So super simple or very active. You always have the AMP VirtIO memory area, which again now is still 512 bytes. And there's always some form of bidirectional notification between the two people involved. And we'll talk about how that works. And then, typical usage of this, there's going to be a single shared memory segment, and all the V-rings and all the buffers are going to go into that single segment. You can use this transport mechanism when you have more flexible memory structure, where maybe the device side can see all the memory of the driver side. This is where VirtIO grew up. KVM, the host, can see all the memory of the guest. If you don't have that constraint, then you can still use the transport mechanism. Some of the problems I talk about later you won't have. And you may have more than one shared memory segment. You may have a couple of shared memory segments. On an AMP SoC, it would be a good idea to have a shared memory segment for on-chip SRAM and a shared memory segment for DDR, because different types of data structures work better in one versus the other. You also may have an IOMMU, or in Zen you have page grants. This allows you to be freer with the memory that you use, but it's then guarded by the IOMMU or the page grant mechanism. So the problems we're dealing with, if we just look at the transport level, we have one of the problems is initialization delay. In traditional VirtIO, KVM is running, the device is there before the guest ever starts. So in an AMP system, maybe they're both booting at the same time. So you're kind of racing with each other. So this is why I talked about a bootloader filling memory with zeros, in the shared memory segment. The bootloader fills it with zeros, then both systems can boot in parallel. When the device side is ready, he's going to populate the header structures. The driver is not going to try to use the device until that's ready. And then we're going to use a different magic and version combination for VirtIO AMP so that the driver side knows that that's going to happen. He may know that already because of device tree or some other mechanism, but this is suspenders, belt and suspenders. And then there's the problem of the index-based configuration. If you look at VirtIO MMIO, you configure one vert queue at a time. You write an index and say, I'm going to configure vert queue 1. There's some device side implement information that you read, and then you configure where you're going to put the V-rings for that vert queue, and then it magically is done. in the AMP system, what you're going to do is you're going to write the index, you're going to send a unique notification that says, I've written the virtq index. You're going to wait for the response. You're going to read any information from the device. You're going to populate the virtq information, and then you're going to send a notification that says, I've updated the virtq information. And so it's got this handshake between it that that works through notifications as opposed to the magic memory that the hypervisor did. And then that kind of gets into the notification. In memory, there's a unique memory notification structure that can be used. So you get these fine-grained notifications. And then there's a shared level of notification where on an AMP SoC, it could be just a register you write to cause an IRQ to the other side. On the PCIe, to the root complex, it's always going to be an MSI, and probably there's an MMR you poke to cause an interrupt to the other side. And then on Zen, we're going to use Zen events. That is a hypervisor call, but it pops into the hypervisor and then pops back out. So it doesn't have this hang on to the virtual CPU problem. Config changes. There's no great solution for VirtIO, the MMIO-based AMP. Again, it relies a little bit on hypervisor magic. There is one thing we can do, which is to say that when the generation counter for configuration is odd, it means the other side is changing it, and you should reread. This is sort of an enhancement to what's already there. On the driver side, you're supposed to read the generation counter, read the data, read the generation counter again. If they're not the same, you're supposed to retry. This is an enhancement or an extra condition to it. If it's odd, you're also going to do the reread. Okay, so that's the transport level. Now, maybe you don't have any of the memory problems that I talked about, and all you need is the transport level problems. Well, great, then you're done. But if you have that single shared segment that many of the AMP systems are going to have, you have the memory problems also. I say this slide is fuzzy. It's fuzzy because we don't have a concrete plan for how to solve these problems in the kernel, when the kernel is the consumer of this. These problems are fairly easy to solve on the RTOS library or in QEMU, where we have a little bit more freedom, but we got to figure out a good structure to fit it into the kernel. And when I talk about the change of direction, I think there's some help here. But the problems that we're dealing with are in VirtIO, as defined by the standard, all the V-rings, all the buffers are communicated with driver-side physical addresses. That's no problem for KVM because he knows the complete layout of physical addresses for the guest. In an AMP system, you may not have all that knowledge. So there's the solution that we're going to implement first is just give the device side more information about the driver side. So we'll have this can either be through device tree or a rendezvous memory structure in the shared memory structure where the driver side populates. This is where I see this memory segment. You know how big the memory segment is, so you can calculate everything else. So that's one problem. Another problem is the vert queues and the buffers. If you have constrained memory, the vert queues and the buffers need to be allocated from that constrained buffers, the constrained shared memory segment. In the kernel, this probably looks like a device-specific DMA pool or something like that. That's why I say it's a little fuzzy. It could also be that you doing copy operations, and that's where the software I/O TLB comes in. It's also called bounce buffers. So the driver side definitely needs changes to address this. And then also on AMP systems, you can have coherency issues. Maybe you don't have coherency issues. If they're both, coherent SMP capable and your hypervisor has mapped it correctly, then, it's magically coherent. You don't need to worry about anything. But if you're actually talking to an MCU on chip, maybe he isn't coherent with your caches. So the MMR space, best to use uncached memory for that. For the buffers and the V-rings, you're gonna have to use the DMA system to do the manual cache ops. Some more modern chips, the coprocessors can be IO coherent. So this frees up Linux from having to worry about the DMA operations. And then the coprocessor side can either have it uncached, mapped uncached, or he does the manual cache ops. And again, I talked about you may not have all these other issues, but these are the problems that we're dealing with. That's not what I want. So the status of this work is not what I was hoping it to be. What we do have is this presentation and a white paper that describes this protocol in a lot more detail than I can go into here in the presentation. We do have previous implementations and prototypes of the VirtIO MMIO that I'll show you in a second. But what I had hoped to show you today was take all those previous demos and prototypes and wrap them up and at least show Zephyr to Zephyr, Zephyr device to Zephyr driver running under Zen and implementing this full protocol. I ran out of time, got pulled into a different project. It didn't happen. So what I do have is with my repo here, you can at least, it's an easy getting started for running Zephyr on Zen under QEMU. It should be easy to set up and try out some of the demos. You can run Linux and Zephyr in DOM-Use started with XL, or you can, there's several DOM zero-less configurations that use U-boot to start all these things up at the same time, and all those are there. I will land an event exchange with shared memory system using 2 Zephyrs and shared memory and events, but it didn't make today, so sorry about that. But it will show up at this repo when it does. I talked about the previous demos. What we've already shown in the past and just recently got rebased and redone, we have in OpenAMP libraries and branches, we have VirtIO, Zephyr using VirtIO provided by QEMU. So this is not AMP VirtIO, this is traditional VirtIO MMIO, but this is Zephyr being enabled with VirtIO. We also have a previous version of AMP VirtIO using Zephyr VirtIO device drivers, consuming VirtIO devices provided by Linux user space in a fork of KVM tool. This is a previous version of AMP VirtIO where there's a little bit of prior knowledge about what the other side is expecting and doing, so not all the negotiation and stuff is happening, but it does kind of show the concept. And then yet another demo is we have the ST demo where the M4 is providing a VirtIO I2C device, and the Linux kernel is consuming that device from the M4. And again, this is using sort of a prototype of the AMP VirtIO. Doesn't, in that model, the memory of the device and the memory of the driver side are the same, so it's not dealing with that. And it's using a single notification for back and forth, but it shows the concept. And then I talked about this dual QEMU setup to simulate PCI-based systems. We have RP message nailed up between 2 QEMU instances over this Ivy shared memory. So that's another demo that we have. Oops. So I talked about probably doing a change of direction. As I walked through that, you may have detected that there's a lot of round trips involved in this, in trying to simulate VirtIO MMIO. And as I was writing all this up, it's like, this is a little crazy. All I'm really doing here is creating a poor man's message-based system. Why not just create a message-based system and forget the alignment with MMIO? We've since learned that other people are thinking along the same lines, and so I think this is more likely to happen. So this is something, so drop the alignment to the VirtIO MMIO, keep the notification model, and keep the rendezvous data structure, and then define in memory, in shared memory, a mechanism for passing messages back and forth instead of these fake MMRs. And then the messages that will go between the two sides will be things like the driver will say, set vert Q5 to this size, here's the 3 physical addresses that you need to know. And then the messages themselves, we're thinking about the vhost user has sort of a message-based interface, and then this other VirtIO transport that I mentioned briefly at the beginning. There's an IBM, I guess 360 power. No, it's not power, but mainframe architecture has VirtIO, and it's called VirtIO CCW. It's also sort of message-based, so that's another place to look for alignment on what these messages should look like. So we're looking to switch to a message-based transport and hopefully align the messages with other people that are looking at the same sort of thing. Yep. So the things I talked about today involved a lot of people. The demos, each of the previous demos were done by different people. All the credits are up here. We have I am rather new to Zen, so I needed some help. And I got that help from AMD Xilinx and Stefano and Michael, their credits here. And we do have some stickers for the OpenAMP project, and hopefully you can kind of see that we have represented somebody from Zen, somebody from Linux, and somebody from the Zephyr with the kite and the Panda and the Linux. So that's kind of the concept behind the sticker. So I think that's it for today. That's what I have prepared. So we can open it up for questions. I know it was fast. Did I answer the questions about why are we interested in doing this? Or do you still have questions about that?
Yeah, I don't know if it's a relevant question, but I've just had one. I had one encounter with OpenAMP and RP message on a Xilinx. It was not the Sync MP; it was just the Sync 7000.
Okay.
Running without a hypervisor and no firewalling on the memory, but it was my task was to upgrade from the Xilinx forked OpenAMP to the mainline one, and that was kind of a pain because of lack of documentation and getting into stuff for the first time. So now you're talking about changing it all again, and then maybe I have to do it one more time.
So the traditional users of the OpenAMP library are using, most often from the RTOS library, they're using the RP message implementation. So we're not touching that. We're not taking away, so that type of VirtIO is called VirtIO remote proc. We're not touching that. We're adding other VirtIO transports. It's kind of, in the past, VirtIO, RP message worked over this VirtIO remote proc and nowhere else. It didn't work over VirtIO MMIO. It didn't work over VirtIO PCI. Another thing that will happen as we do this work is RP message will work in those other places also. But so the Zinc, I'm not sure how, I kind of feel your pain, but I think it's also a little bit of older code base. For the Zinc MP, AMD Xilinx is kind of keeping it up to date with the upstream pretty well. But it is a portable library, so it's up to the vendors to implement it. I would say that's one thing nice about Zephyr is you port OpenAMP to Zephyr, and by the way, it's already done. As long as Zephyr works on your chip, you know, it's a lot easier to get this functionality working, right? So that's kind of why we chose Zephyr as the reference, because it's, you know, it works on an M3, it works on an A53, lots of QEMU models.
Is in a typical ARM SoC where you have normal world, secure world, is there any, where does that fit into this model, if at all? Maybe it doesn't, but.
It does. I think there's other people working in that area that will complement this. But you could certainly imagine doing this exactly as I described, replacing the bidirectional notification with some, you know, SMC kind of thing, right? But yeah, you could make it work exactly like I talked about. Just today I heard about somebody wanting to do a I2C driver. They wanted Secure World to own the I2C bus. You know, publish it as a VirtIO I2C and let Linux use it from there. And maybe have a firewall in there that lets them get to some of the I2C devices, but not all of them, you know, that kind of thing. I think that's a prime example of this.
Could you please share more on this? Like, why not use VirtIO RP message, that VirtIO remote proc, and where does this fits instead?
Right. So the question, if you couldn't hear, was why not just use services on top of RP message instead of doing this extra VirtIO stuff? It's a good question. Some of the users of RP message are just MCU to MCU. And, you know, I don't know as VirtIO net and VirtIO block have a lot of value in MCU to MCU. But certainly whenever you have the Linux kernel involved, being able to tap into that existing ecosystem of drivers and not having to introduce a new RP message for networking. And when, by the way, RP message is really meant for control messages, not jumbo frames of network, right? So to me, it seems, you know, a former employee of mine used to do network acceleration on an R5. And then there was this big complicated system to get Linux to use that. It would be very natural for the R5 to expose a VirtIO net to Linux. And if Linux is VirtIO AMP capable, it would just know how to talk to that. And it would be very natural for it to start using that. There's a lot, you know, it's basically reuse. If you have an ecosystem where these other types of VirtIO devices are already supported, wouldn't it be great to support them in an AMP system?
So in that, what is the discovery mechanism like? How does Linux know that the remote code is telling to has support for Voltaire NAT, and what is the discovery mechanism?
Yeah, so several. It can be just nailed up in device tree. So in device tree, you could say, here's a shared memory area with the VirtIO MMIO structure, and here's the mailbox to send the notifications to. It could also be this rendezvous data structure. You could go looking at that, and it's kind of a lightweight sort of, not device tree, but kind of device description. It says, here's the MMIO devices that you can use. You could also imagine maybe you have an RP message and you exchange RP message device control messages that say you have a new MMIO, VirtIO MMIO device and it's over here. You could imagine a number of ways to do that.
Okay, thank you.
I think we're at time, aren't we? One more question.
So you mentioned about the dual QEMU, right?
Yeah.
Do we need any tweaks to the QEMU in order to make it to work, or stock QEMU works out of box?
Stock QEMU works out of the box for that. A tip, if you want to run Zephyr on Zen on QEMU, you need QEMU 8.2 or later. That was a very hard-won piece of knowledge because it just locks up. QEMU just locks up on earlier versions. I don't know what's happening, but if you run my demo, I have I packaged a version of QEMU 9 to make that work. But if all you're interested in is running 2 Linuxes with the IV shared memory, that should work on any. You do need the IV shared memory server. Not everybody publishes that. It is built out of the QEMU tree. The Zephyr SDK ships it in the Xilinx version of the IV shared memory server is the same for everybody. It has been for years, so any copy of it should do you.
Okay, cool, thank you.
All right, we'll call it quits there. We do have stickers at the back, so if you want a sticker, you can talk to Natalie. Thanks, guys.
Oh, I'm not sure I'm supposed to start because they did not start the recording. Oops. Hmm?
They already started recording.
No, that's the PowerPoint.
Okay.
I think I'll go ahead and start. Am I audible? Okay. Yeah. Hello, everyone. Good evening. I'm Vaishnav Achat from Texas Instruments. And today I would like to talk to you about accelerated porting of Linux, U-boot, and Yocto for production-ready embedded systems. I work with the Linux team at Texas Instruments, and Texas Instruments has a long history of contributing to open source, and we think upstream and open source ecosystem in the device architecture phase itself. As part of my, I think the HDMI cable is loose, sorry. Hey, sorry. So as part of my daily work, I work with Linux kernel and U-boot development for TI processors. I'm also the maintainer for TI platforms in Sapphire RTOS. So Kirti is the co-author of this presentation, and he'll be joining with us over remote. Kirti works as a software application engineer with TI, and he has supported multiple customer platform bring-ups in his more than last 15-year career with TI. And he was also an active contributor to the Linux kernel, working on bandcap and GPIO drivers. So in this talk, we would like to share the basic steps you will need to do to get U-boot, Linux, and Yocto running on your platform from the lessons we have learned from multiple past bring-ups and practices we followed to make our journey efficient. So the talk is split as follows. Initially, we will discuss a few challenges on why it's not straightforward to port and support different permutations of hardware you have on U-boot, Linux, and Yocto, in addition to the basic bring-up challenges. And then we discuss on steps to bring up U-boot, Linux, and Yocto on a new hardware platform where they, on a new SoC, and then we discuss on how we bring up U-boot, Linux, and Yocto on a new hardware platform where the SoC vendor have already provided you the support. And in the end, we also look at some case studies of efficient tools and techniques that the recent upstream uses. And the most of the focus here is on bootloader because that's where the people face difficulties during new platform bring-ups. So there are a few disclaimers. So we go through a few references and examples. So we just say it's one of the ways you can solve the problem. We don't claim that as the best practice. All the examples we discuss here are picked from upstream accepted solutions. And the accelerated porting, we mean, so we have talking about techniques and strategies to reduce duplication of effort when adding new platforms and not getting the fastest port out. So coming to the motivation of giving such a talk. So there are already a lot of talks available about how to bring up U-boot or Linux on a new platform. So we want to focus not only on the bring up, but maybe shed some light on the challenges that SoC manufacturers and the hardware platform vendors are facing. So bringing up the U-boot and Linux and Yocto on a new SoC and new board can be challenging. And in addition to the normal challenges of getting things to work, we also have the challenges of supporting multiple SoCs in the same family, different SoC variants. There can be cut down SoC versions. And these are the challenges you can face as a SoC manufacturer. And on the boards or hardware side, hardware platform side, you have different kinds of board architectures. You have a single PCB EVM. You can have a SOM plus baseboard kind of platforms and different. And there can also be system in packages where you have SIPs, where you have the SoC, the DDR, the PMIC, RTC, everything packaged into a single package. So how do we support all these combinations in a sustainable manner? So whether you are a SoC manufacturer or a hardware platform vendor or a customer who want to solve this problem, you usually have a common goal. So you want to introduce new platforms with minimal duplication in source code and effort. And now the customers are not demanding just a drop of software when the SoC is released. So they want the product cycle, the support continues along the product cycle, which spans more than a decade on most cases. And we need to have a scalable implementation where someone new can add a new hardware platform based on your SoC that you're putting. So just to shed some light on these challenges we are facing in TI. So if you look at the TI AM6 SoC family, so we have different variants of the devices. So there can be a variant with single A53 cores. There could be variant with 4 A53 cores. There can be variants with a GPU. There can be variants without PRU. PRU is a real-time controller in this process. So there are multiple combinations from the same SoC family. Then there can be system in package where the DDR, the PMIC, the RTC, EEPROM, everything is integrated into the package. And then we have the exact same SoC, but maybe due to the eFuse configurations or the OTP configurations, they behave differently to the software. For example, the security enforcement. So some devices, based on the permanent configuration, they don't need signed or encrypted images to work. And some devices, we need signed and encrypted images to work. So when you look at it from a high-level perspective, these are the exact same devices. But when you go and look at it, the bootloader, you need to have a complete different signed images to make these two devices work. But how do you go about adding the support without duplicating the effort? And if you look at the hardware platform or board side, you can have single PCB EVMs. And if you look at the right end, you have two devices that are very similar in features, but goes to two different markets, the industrial and the automotive market. And you can see there are differences in the expansion connectors and all. So then we need to have a way to support all these combinations in a sustainable manner. And if we don't have a strategy, we'll just go and duplicate all this and create a new platform, consider all of this as a new platform. And that becomes a mess to support later. So if we have fixes coming in, you might miss in one of the platforms, but underlying hardware is actually similar, or the SoC is similar. So first we'll talk about how we'll work on bringing up a new SoC. So we can think about bringing up the software on an SoC when we have the silicon available. But sometimes it's too late to start thinking about software and the silicon is available. For example, you might have some critical use cases that you want to validate before the silicon is available. So you can, a commonly used practice in the industry is to start validation of software on a simulator where you have the implementations of the SoC in software, but it's not a cycle accurate model and you cannot do performance analysis or maybe do a complete use case analysis. And you can maybe develop frameworks and accelerate your initial development faster. Then we can do the software validation on a hardware emulator where you have cycle accurate models and you can do the actual device driver development. You can boot up Linux and boot up U-boot and Linux and validate your stack. And even you can run performance and use case analysis there. And if you have a strategy to perform the software validation on a simulator or an emulator, it can actually accelerate and help your software bring up on when the actual silicon is available. So there was an interesting talk during the Embedded Linux conference last year, where my coworker Brian explained how we perform mainline Linux development on our platforms before the silicon is available, and how that's helping us making the complete process of software bring efficient. So coming to, you have a new SoC and you want to bring up the bootloader, and we are focusing on the U-boot. So first you'll need to understand the boot sequence or the boot architecture of your platform. So your platform may have different boot architecture. Your ROM may load up the startup core in different ways. So I'm taking an example where we have an ARM v7 R5 startup core and how the U-boot starts up. So we have the entry point at the start.s assembly code where we have the architecture specific, and sometimes it can be even your CPU specific initialization, where maybe you have a dual core cluster of R5, you disable the second core for boot up, all those things you perform there. And it's the minimum basic functionality you need to reach to the U-boot board init F. So how did we reach start.s? The entry point there, so that's what your ROM, the bootloader does, and that will be different according to different platforms. But the rest of the flow in U-boot will be similar for even if you go to different architecture also, it will be looking similar. So on most of the SoC platform you want to add supports, you will just need to add support on this something called a board init F. That's where you have to initialize your SDRAM and your serial console. But it might not end there. So if in order to get your serial and your SDRAM, you might need to have your dependencies also initialized and set up properly. And you don't have BSS, or you cannot have global variables in this board init F, and you have the stack in SRAM. So you are having a very limited environment to just initialize your DDR and serial console. Then U-boot returns from the board init F, and it jumps to the board init R. So at this point, you have your DDR initialized, and your stack and global data is relocated to DDR. And in the SPL stage, we don't relocate the code to DDR, but in the normal U-boot proper stage, we execute the code from the top of the DDR. So most of the bring-ups, you will be, the first challenge you'll be facing will be fixing things in the board init F. And that's where you have to get your DDR initialized and your serial UART initialized. So from the U-boot documentation, only suggests to initialize the preloader console or the serial console and just the DRAM. But you might need dependency sorted out and in order to initialize the DDR and preloader console. For example, during the startup, the MMR registers might be locked. So you might need to perform an unlock to write to those registers. Then there could be architecture-specific initialization. For example, if you have a R5 kind of core, you need to initialize the memory protection unit regions according to your configuration. Then for example, if you look at the multi-core heterogeneous processors, there could be a chance that you have a system controller or a central controller which manages power clocks and all, and there could be a security controller which is common to the SoC. So you might need to load the custom firmware and start up and initialize those remote processors before you are actually able to do any general purpose functionality on your bootloader. Then there can be firewalls. So the memory regions, the configuration register regions could be firewalled and locked, and you might not have access to write to those regions or read back from these regions. So you might need to configure firewalls to enable your bootloader to function properly. Then you might have the same build of U-boot working on different hardware platforms. For example, we have the same U-boot build working on one of our EVMs and maybe smaller starter kits, all the same exact U-boot build. So we'll pack the different device trees and different DDR configurations to the same image, and we'll be picking the device tree based on the board detection logic. So you need to do all these before configuring the DDR, because the DDR configuration usually is a very big chunk of registers, right? And it depends on the controller. And only if you select the correct DDR configuration according to your platform, your DDR initialization will be successful. Then you can come to the preloader console initialization. It's assuming you already have a serial driver present, and now you have all the dependencies sorted out for having the power, clocks, pin marks, everything for your serial. And then you go to the SDRAM initialization. And there could be also cases like you want to have some miscellaneous or advanced features that you need to enable very early at the boot. For example, some features like AVS, the adaptive voltage scaling, you need to have that set up as early as in the boot, which is the hardware recommendation. So you might also need to implement functionalities like that. So that's what you will need to do to customize your board in ITF. You'll need to initialize the DDR. So I'm not going to the detail of the specific DDR control configuration. And now I'll go to some details on how you can have, so U-boot provides a lot of weakly defined functions in the bootloader implementation, which you can override to customize for your platform. So first one of them is the SPL boot device. So most of the platforms will have different boot modes from where your bootloader is booting from. And your hardware may have maybe registers or some configuration which you can read from and tell U-boot that you are booting from a flash on a SPI, or you are booting from an MMC SD card, which is necessary for U-boot needs the context to fetch the next bootloader from which media to boot from. Then we have SPL board in it, which is also a weakly defined function you can override in your board specific files. And for example, your PMIC could have an error signaling module, and you perform the initialization of the ESM in the board init. Then you might need to perform fix-ups based on your platform. Maybe you do the board detection based on you have multiple boards running the same configuration, and you want to fix up. For example, you have a controller that's muxed out. So you have something like a SPI controller, which is muxed to 2 different SPI flashes, and there is a mux switch on the board. And you need to tell U-boot to initialize one of them based on your dip switch configuration. So you need do these kind of fix-ups in your board init, and in the perform fix-ups. And you need to tell U-boot the size of the DDR bank information. You can either fetch it from your device tree, or if your hardware provides other features for auto detection, you can fetch it and tell U-boot what's your DRAM bank information. Then we are coming into so you are booting from U-boot, you are booting to the high-level OS or Linux, and you need to fix up the device tree based on your platform. So for example, you have something called FT system setup, where you want to fix up features of the SoC. Like we discussed earlier, that there could be device variants with lesser number of application cores, device without a GPU, and all those. So we can fix up the device tree using the FT system setup override function. And if you want to do a board level fix up, for example, we discussed the different SPI flashes muxed and connected to a single controller, and you need to select it according to the dip switch configuration. So you will use the FT board setup override for this. So these are the main override you will need to define in your board specific or the SoC specific platforms to get your changes working on your custom platform. So with this set of changes, you should ideally be getting a U-boot, working U-boot, because if you look at the board init R or the U-boot proper, most of the code is not platform specific. It's all the common code. And if you have the device drivers for your boot media and the peripherals that you use during the bootloader, and with this set of overrides, we are able to get most of the platforms getting up to your U-boot proper console. And now next I'm switching to how you can bring up Linux on a new platform. So the discussion is around platforms where you are not introducing a new platform, where you are not introducing a new architecture or new device family. Our discussion is around where we have a device family where present and we are adding a new SoC to the same family. So bringing up Linux once you have U-boot working is mostly easier because you have access to all debug utilities and you don't need to have make a lot of changes to get Linux working. So one of the things you need to take care before trying to get Linux working is to make sure that your SDRAM is stable. So if you face issue, if you don't have a proper stable DDR configurations and you start bringing up Linux, you can see random failures happening when you boot up Linux. So you need to make sure at the U-boot proper stage itself that your SDRAM is stable, and U-boot provides a command called mtest, the memory test, and you can configure to perform read-write tests on your SDRAM and make sure that it's stable. So if you want to add support to a new platform, it's adding the new bindings for your platform and then adding your device tree. So initially it's recommended to start with a minimal device tree where you have your the cores that are running Linux and also your serial console and minimal peripherals, so that you don't face issues during boot and you see failures during boot. So, and then it's also recommended, so we can have your init file system taken from different boot media, but if once you have the U-boot brought up, it's recommended you can try loading a RAMFS, minimal RAMFS, and get to a minimal RAMFS console by preloading and configuring that the RAMFS address and size in the device tree. And then one of the things that you need to take care of is you have a minimal device tree, but some of the times the same SoC family could have, the drivers could have something that's not directly visible from the device tree. Like it might not be directly visible that some features are enabled. For example, you have the DVFS, the power management drivers, where the implementation and how they are enabled is using the same compatible as your SoC. So sometimes when you bring up a new hardware platform, your SoC vendor would have already put that compatible in the driver, but you don't see exactly in your device tree that you have DVFS enabled. So you need to look for things like that. And some of the drivers use the SoC identifications to configure parameters. So you might need to implement your SoC identification implementation so that your there could be some driver data that's picked based on your SoC ID or JTAG ID. And if you are seeing any failures, so usually it's recommended to start with the ARM64 or your architecture specific default config. And if you're seeing issues with the default config, it's recommended to maybe disable some of the advanced features like runtime power management and enable more debug features where you have access to more debug utilities. So for example, I talked about you might have some hidden things that's getting enabled without you even knowing or putting up in the device tree. You try to create a minimal device tree, but there are things that got enabled because the SoC vendor has put those as defaults that are enabled for the SoC. One example is the CPU FREC or the DVFS power management, where the SoC vendor usually puts your SoC compatible as in the driver match, and as soon as you create a new platform with the same SoC compatible, the match happens and you have your DVFS enabled in your basic bring up, which you might not actually need. You might not be intending to do that. So you need to be careful about these things in the platform, the device drivers. So these are the main basic things you need to do for bringing up Linux. Now, next we're going to switch to how you can bring up Yocto. So for a basic bring up, it's recommended you use your SOC vendor's same file system and do the customizations later once you have a system that's boots up first. So for the devices that we are discussing where there is already the families, the SOC family is already supported and or the SOC is supported and you are adding a new hardware platform, the Yocto, the machine configuration for Yocto should be very minimal, and you should ideally need to only add overrides necessary for your particular platforms. So for example, you might need overrides for your boot image files. Maybe you have some security enforcement. So you might not be using the exact same device. Sometimes the default platform might be a secure device and you are switching or bringing up a general purpose device. So you might need to do that. And also you might need to add the extra recommends package list where you are adding the list of packages that needs to be installed as default of the image. And most of the times, if you are bringing up a new SOC, you will have the binaries. So the firmware binaries, you can have a system controller, you can have different remote processors. All those firmware binaries might change according to your new device. And whenever you will have, so you need to make sure that all of the recipes you need from the SOC vendor, so have the compatible machine, you are adding the compatible machine entry for your platform to all of the recipes you need so that it's also getting included and built. So these are the steps maybe summarized for a new SOC, adding support for a new SOC. So now we can have a look at where you want to add a new board support, or a new EVM or a support where the SOC support is already served. We'll focus on the deltas, what you might need to do for a new board support. So, on the board specific changes, mostly it will be, so your power path or the power tree that you choose might be completely different from what your reference or what you have it in the reference BSP. So you need to make sure that you have the right set of changes for your PMIC, or maybe you have discrete regulators, so you should have that power tree properly configured in your device tree. And most of the cases when you change the boards or you may pick a new DDR part, you will have a different DDR configuration that you might need to update for your platform. And you might have to choose to have a different serial console than what the SOC vendor provides. So you should be careful that you need to make sure that if you are switching the serial console, you should switch the pin marks. You should make sure that the power, clocks, everything for the serial device is available. You are making the right changes to have that available. And if you have the choice of selecting the boot media before, then it's recommended that you choose a flash or the flash media where you can flash it independently out of the board. So sometimes you have a SPI flash on the board and you don't have a way to properly flash the SPI without the board brought up initially. So if you have an MMC, if you can afford to have a SD card boot mode and you are flashing the image just to the SD card from outside, so it helps you ensure that there is no issue in the process where you write the images to the boot media. If you cannot afford that, UART boot mode is one of the simplest boot mode that U-boot supports, and you can map the exact same console where you get the boot logs to get your binaries over X modem or Y modem protocol and continue boot up. It's very slow, but it's very simple, and there is very less chance of failure happening in UART boot mode. So now with those steps, you will be able to get U-boot working. And if you are trying to bring up Linux on a custom board and where the SOC support is already provided by the vendor, the first and foremost thing you will need to ensure is the DDR stability, and you should make sure that your DDR is stable at your U-boot console itself using the memtester command. And it's recommended to have the early console print so that if, let's say, your boot up is failing before Linux is able to initialize your serial device. And you can get some console prints if you set up the early consoles. And how that works is U-boot sets up the serial device configuration, and Linux just uses those the RX and TX registers and just writes to them. Linux will not initialize the UART, but it will use a pre-initialized UART and give you early prints in case your UART initialization itself fails during Linux boot up. And also make sure to have your proper boot args in your device tree, or if you are passing the boot arguments to through U-boot or through device tree, you need to make sure you have it correct. And if your init or the boot media is not properly, the init is not provided properly to Linux, your boot can hang and stop before the init starts. And also, again, similar to doing an SOC bring up, it's recommended to have a very minimal device tree. And you can have a big device tree, but keep all of the peripherals and the nodes that you don't actually require for a minimal boot. It's recommended to keep it disabled and enable one by one and validate them. And also you might need to, if you have a multi-core, heterogeneous multi-core processor, it's better to have all of the remote processors also disabled so that it does not, those cores does not go and maybe overwrite anything that Linux needs on, overwrite anything on the DDR that Linux is using. And these are some of the issues that we have seen the customers reporting when they are doing an initial boot bring up. So one of the main problems that it's very difficult to debug is you have DDR stability failures. So you will have your Linux crashing at very random places, and it might you might not be able to reproduce the crash sometimes. So it's so we usually recommend to run the memtester in U-boot maybe an overnight or over a weekend. You do it continuously so that you have ensured that your DDR configuration you have is stable. And sometimes, so we discussed this already, sometimes the SOC vendor might enable something, you don't actually see it on the device tree, like the DVFS or the configs may have runtime power management. You can see failures due to that. So it's recommended to have a minimal config to so that there are no failures due to those. Then you have you may even have your console failing. So there could be multiple causes for a console failing. You might not have power, clocks, or pin marks for the console, or even maybe the interrupts for the UART instance are not getting registered. So we are just going through some case studies or examples and what some advancements happening in upstream that helps you streamline and make your process efficient. So first thing is, so we discussed some challenges where you have a lot of SOC variants, different configurations, and you need to add the support for these platforms in a sustainable manner. So one of the challenges is you have different kind of bootloader images that you need to support for a same SOC family. So you have a general purpose device, you have a secure device, and you need to create the bootloader binaries without maybe having the signing or the encryption steps customized for your platform. So U-boot has a tool called Binman, which solves this problem through device tree configuration. So you describe how you want the binary. So you might need so for example, here you can see that the content field of this, so that the TI boot 3 is our initial bootloader. And in this description, I'm describing the contents of that bootloader. You need to have the U-boot SPL, then you need to have the certificate, then you need to have some of the configurations that your ROM or your bootloader might use. So you can pack all these and you can create multiple permutations of this image according to, let's say you have a general purpose device, you need to pack these components. You can have a secure device where you need to have a different set of images packed together to have your binary. So the binman solves the problem of having like maybe custom signing scripts, and you can have different platforms supported from a single binman DTSA configuration. And usually if your SoC vendor provides for all the variants, if you are doing a new hardware platform, you might not even need to touch the bootloader image generation. Then till maybe the 6 months back, the U-boot had a separate device trees that has been continuously been synced with the Linux kernel. So recently there is a feature being added called OF upstream. There was a talk today morning about that by Sumit. So the main crux behind OF upstream is that there is a device tree rebasing repo that's maintained by the Linux device tree maintainers. So they have a rebased device tree that other projects can make use of. And U-boot is moving to have the device tree rebasing repo as a subtree inside U-boot. And we don't go and add new device tree for separate device tree for U-boot like we did maybe 6 months back. So you don't need to keep rebasing and syncing device trees each kernel cycle to U-boot manually. So you just need to get your device tree accepted in the mainline Linux kernel, and it will come through the device tree rebasing repo to your upstream U-boot. So you don't need to upstream any U-boot specific device tree unless you need to have some U-boot specific overrides. So then another challenge is you need to support different ways of booting. So you need to have maybe support booting Android, and you need to have some configs that are specific to booting Android. But you don't want to bloat your normal configuration with this Android configuration. So U-boot supports something called the defconfig fragments, where you can keep the config specific to the Android boot as a fragment, and then use that along with your base config, and have a system where you don't bloat the default configuration with the Android configs, and if you want Android, you just apply this fragment on top of this default configs. Now coming to, so we discussed a lot of challenges. So we discussed we may have platforms without GPU, without lesser number of cores, and we discussed overrides that U-boot provides to fix up your device tree. So this is very much useful in cases where your device variants are indifferent to U-boot. So if you have a 4 application cores or 8 application cores, it does not matter to U-boot at all. It's a bootloader that just runs on single core. And if your platform has a GPU or not, or an accelerator or not, it does not matter to U-boot. In those cases, you just need to fix up the device tree that you pass to the Linux kernel, and you can use the FT system setup because it's a SoC specific features that you are overriding. And if you are overriding board specific features, you will use the FT board setup override. And this helps in not duplicating the device tree for each cut down or each variant of your device. So you can make use of your device features. Your device may expose some capability or feature registers where it can tell you how many application cores it has, or it has a GPU or not. And you can read those registers and override your device tree according to that. So now you have a superset or a subset SoC, which you have already upstreamed the support, and you have the support available. Now you know that your device is a subset of or superset of the device. So normally you can maybe just forget about reuse and go and add the entire new device tree as a completely new SoC. But it's useful and recommended to have an analysis whether you can reuse existing device trees. So for example, this is one of the recent platforms we upstreamed. where we have the base subset platform already present in upstream, and the superset platform has additional features and it's memory map compatible. So we don't just go and duplicate the entire device tree. So we just inherit the device tree of the subset or superset platform, and you either delete nodes from the platform or you add the overrides. Okay, so that's the end of the case study. So there are a lot of useful, U-boot provides a lot of useful utilities or commands where you can maybe check the pin marks, toggle GPOs, which might be useful in bring ups. So let's say you have a device that you want to bring up, you need to toggle the reset of the reset GPO of that device from U-boot. So I have listed down a few commands that are useful during bring ups. I'm still updating the list, and so this is useful only if you have you are reaching up to the U-boot console. So many times you might not even reach there. You might even get stuck in your board init F before your serial console is initialized. So at that times you will need to use a JTAG debugger and go and debug. So there are some details on the link on how you can debug U-boot and Linux using OpenOCD and with GDB. So just summarizing whatever we discussed. So if we start the bring up or the validation on a simulator, it's very helpful to validate the software when your silicon arrives. And it's best to start your baseline within the upstream baseline. So whenever you start your preparing your code base for your new device, it's best to start with the latest upstream baseline so that you can, once you have your device ready and you make your changes, you can easily send those, make the changes and send those patches upstream. But if you pick a very old kernel of your, or if the vendor tree is very old and you start with that tree, and you might have the inertia to not port those patches to the upstream and not post it upstream. So it's better to start upstream, start using the upstream code base as early as possible. And if you are adding new features or new subsystems or frameworks, it's recommended to have that posted upstream first. And if it's the more complex the feature is, it's better to have this solution posted upstream so that we have the feedback from the community. So if we don't do that and we release those solutions to the customers and the community does not agree with your solutions, it does not look good, and it's very difficult to go and fix something that you have already shared with your customers and the community does not agree with that. And if you are making Linux device tree changes, make sure to follow the device tree coding. The DTS, the device tree has a coding guidelines recently added, which is available in the bindings DTS coding style document. And also make sure to run the binding checks and DTBS check on new device trees you are adding. And even though it might look counterintuitive, it's better to add your Linux device tree first and then have that same device tree derived to U-boot through OF upstream. Or if you are locally developing, you can have the device tree rebasing repo patched with your device tree and use the same device tree as Linux. But if you go, maybe you do the bootloader bring up before thinking about Linux bring up. So, but the upstream does not accept a separate device tree for U-boot. So it might be difficult to fix it later. So it's better to start with the Linux device tree, derive that for U-boot, and continue with the bring up. And also maybe so that you don't miss the features like binman, OF upstream and all, you need to be active in the community and continuously make changes to your platforms according to the standards that the community is offering. Okay, thank you. I'm done with the presentation. If you have any questions. Okay, thank you.
Mic check. Cool. Okay. We'll go ahead and get started. So today I'll be talking to you guys about shipping multiple device trees and identifying which device tree to load for your device. So just a quick introduction. My name's Elliot. I'm a Linux kernel developer at Qualcomm, based in San Diego. Some things I've been working on recently is the Gunya hypervisor. You might have seen my name posting all those patches. Before that, I was doing a lot of kernel build, Android kernel build stuff. And I also did a lot of enablement for GKI for Android in Qualcomm. So just a really quick kind of introduction. So for those who don't know, device trees are a way of describing hardware. The kernel authors these usually. There's other folks who author them as well, Zephyr, FreeBSD, U-Boot, although there's a lot of effort to try and consolidate that, thanks to Sumit's talk earlier today. But usually what happens is the bootloader picks up the device tree and passes it to the kernel somehow. Or sometimes the device tree is appended to the kernel if your bootloader doesn't have support for that. Generally, the kernel doesn't own the bootloader. It leaves it to the ecosystem to package and pick up the DTP that it wants. So you'll see that U-Boot does something different from, say, Android boot process, which does something different from Grub and does something different from Core Boot. And so, we're trying to sort of consolidate how that's going to work, and we'll go through that. Ideally, the DTP would come from firmware. Unfortunately, I think there's a lot of sort of hard realities that make it that way. That's probably not going to happen anytime soon. And I'd like to try and solve this problem today. Well, not today, but soon, and not wait for vendors to figure out how to get their firmware all sorted out. Cool. So yeah, the talk is about picking the DTB. So maybe you just have one DTB and you just know what board you're running on, and you just say, yep, that's the DTB I want. When you do your build command, you just say pick up SM, QRD or QRB 5165 RB5 DTB. You pass that into your make boot image or your fit image or whatever, and that's what you have. Or you concatenate the image to your DTB, and then you have a concatenated kernel and DTB. That works too. Or maybe you have a multi-DTB bootloader that can figure out which bootloader to pick. And so the focus of this talk is just on picking the DTB. We're not talking about how to package DTBs. I kind of want to leave that to like a little bit of a different discussion. It's just how do we pick the DTB? So why would you want to ship multiple device trees? Device manufacturers might want to ship one software binary to a variety of devices. So for instance, Qualcomm, we want to ship a single software package that supports all of our reference devices for a given generation, and we have a lot of different reference devices. OEMs might want to package a software or have a single software package that supports, you have your iPhone Pro or your Galaxy S22 and your Galaxy S22 Max or whatever, and you want to just have a single software package for that. I think this is kind of applicable to a lot of embedded world as well. It reduces friction when receiving a new board. You just receive a board. I don't know what I got. Well, you probably know a little bit about what you got, but you may not know exactly what board you got. It'd be nice if you could just load some image that says, okay, this has all the Qualcomm DTPs on it. We'll figure out, what DTP to really pick later on. So what kind of differentiation does boards have? They could have different sensors, different displays, coprocessor attachments, so different GPUs, maybe a different modem, maybe a different WLAN chip, different PMICs. There's all sorts of different differentiation that could happen on different boards. And so that kind of motivates why you might want to package multiple DTPs into a single software image. So devices from Qualcomm. We have SOC hardware identifier registers. That's one way that we identify which board you run on. So for instance, we have SM8650. There's a register that you can read, and that identifies that that's the board or the SOC that you're running on. We also have this thing called a configuration data table called CDT, and it answers which reference board is this. So Qualcomm produces many different reference boards, but some of the common ones that you might be familiar with are HDK, robotics dev kit, so like the RB platforms. Auto dev platform is also another kind of popular one now that's coming out. And it also, the CDT, so the CDT will say, this is the HDK, this is the RB kit, this is the auto dev platform. It'll also describe what else is attached. So does it have the vision kit attached for like a RB3 or RB5? Does it have a display? What kind of display does it have? What kind of PMIX does it have? It's not really a device tree. It just is like kind of a number that says, okay, well, this is the device tree that it has. This is kind of data that's stored in EEPROM. You can think of it as just some hard-coded bits that are assigned to this particular device. And generally, hardware features are encoded in the board version. Sometimes they're different identifiers. It kind of just depends on what sort of the vendor feels like doing or what the OEM feels like doing. So for instance, we sometimes will just increment a minor number version to say there's a different Wi-Fi chip or there's a different display. We'll just increment the minor number of the board. Or we'll have an entirely separate field. It's kind of independent. But Qualcomm will have one software package, and you can see I took some numbers, and I found that we would ship 20 DTBs and over 100 overlays. So that means we have over 100 boards that we want to try and support in a single software package, which is a lot. You think that's a lot. It's actually even more than that we support. So we have hardware identifiers, SKUs, and we have even more SKUs than just the 100 overlays that we have, the 100 boards that we have. So the SKU will encode things like DRAM manufacturer and who manufactured the EOSS chip and all sorts of different stuff that maybe software doesn't necessarily always care about all these different things. And demuxing that SKU can require a lot of software updates and firmware to say, okay, well, I know every single time you produce a new board, now we got to go update our software and say, just because we updated the DRAM, we have to go do a software update. So, folks may be familiar, if you're familiar with Qualcomm hardware, we have these old MSM ID, board ID, and PMIC ID. So the Android bootloader ABL will read these identifiers from the CDT and the SOC hardware registers and map them into basically some sort of bit field that's called MSM ID, board ID, and PMIC ID. And our bootloaders will read all these DTBs, and they all have this MSM ID in it, and they'll try and match and say, okay, well, I read the SOC hardware identifier register, and I read the MSM ID, and they both match what I'm expecting it to be. This must be the right DTB. And they'll do this for all of these different fields, and we have kind of a pretty complicated algorithm sitting behind it that isn't all that great, but we're trying to get something that's common. So a decade ago or longer, we tried to upstream the MSM ID, but it was rejected because the kernel doesn't use the MSM ID, and there was kind of this feeling that the kernel should always be using the fields that are described in the DTB. I think that's changed a little bit now recently, but the consensus back then was we should have, if we were going to plug the MSM ID, the kernel should care about the MSM ID as well. So we tried documenting and using compatible strings. I think that's kind of the consensus current upstream approach, is use a compatible string. It didn't catch on. We created this nice format for describing a compatible string based off of all the information that we want to mux off of. And yeah, you can see it just gets kind of, there's a laser here. It gets kind of crazy. I purposely made it off the screen, but and there's even more. This was a decade ago. There's even more things that we want to try and mux off of now. And so one of the kind of key points here is that it requires custom parsing. The CDT is going to encode all the information. You're going to have EEPROM that says this is all the different things that it has. It may be that you always ship a device, this board, with UFS, but your CDT is going to say, yep, you have UFS, and you're never going to need to change and say that, oh, well, now I'm shipping with eMMC or NAND flash. But you want to differentiate that because your DTB is going to change. So how do you parse that string? Do you just say, okay, well, you got to describe all that information, even if it never changes? Well, now you get this really long compatible string. Or you have some sort of like default fallback option, and you try and do all this logic for saying, well, if you don't specify it, then it's okay if it's this value, and that just gets really complicated to do, and that's not portable across bootloaders, right? It's going to pretty much always live in just ABL, and nobody else is going to ever be interested in taking Qualcomm's this. So one of the things we also tried to do was encode that information outside of the DTB into a DT image. So this is kind of similar to what U-boot does. So we just basically lifted the MSM ID off of what was in the DTB and put it into some metadata that was outside the image, outside the DTB itself, into some header file. The problem with this approach was we were still having MSM ID in our DTBs. It's kind of hard to, in your build system, describe, well, this DTB needs this MSM ID, and you have to sort of pull it along in the entire build process, and you might be trying to apply overlays to that DTB during the build process. It just gets really kind of complicated to be tracking that metadata separately from just having it nicely encoded inside of the DTB. So some of the upstream approaches, the first one that pretty much everyone talks about is just use the compatible string. Like I mentioned, it requires string parsing, and that can get really complicated. It requires porting the parsing of that compatible string to every single bootloader that you care about supporting. It's used by, I think, Chromebook. I think it's also used by Tegra, as far as I can tell. If there's anyone else here, I'm sorry I didn't mention you. I was doing research and trying to find upstream people who seem to be doing something that has some format. But yeah, compatible strings also often include the SOC. But board X DTB isn't going to work on board Y, even if they have the same SOC. So frequently you'll see a board DTB that says, well, I'm a Chromebook X, and I'm also a QCOM SC blah, blah, blah chip. But you're not that same QCOM SC blah, blah, blah number SM, like say SM6115, isn't going to work on some other board that is also based off of an SM6115. So if you have this fallback of compatible strings, it's going to get weird if, say, you don't find a match. Another approach that's kind of been talked about was just put all of your nodes in the DT and let the bootloader figure out what to enable or disable. The problem with that is it creates a contract between bootloader and device trees, and if you're not using, say, U-boot or an upstream bootloader that definitely is relying on Linux, it's not going to work as soon as you want to update the device tree to not have a node, or you want to add a new node, and the bootloader is expecting it to have some node, and fix-ups are just going to start to fail. What do you do when the fix-up fails? So some downstream approaches. I've talked about what Qualcomm does. It's MSM ID and board ID. It's a bit field containing some magic constants from some ROM region. As far as I know, Google Pixel has a very similar approach to Qualcomm. They have a field called sock ID. Android has this DTBO image metadata. It adds an optional ID, revision, and U32, or some custom fields. It's basically kind of what I was describing earlier with the QCDT image, where you just encode that MSM ID into the metadata of the DTP image. So U-boot uses, as far as I know, the file name to match the DTB. So in U-boot, there's this property that says, is this the right DTB? And it just matches. It's kind of similar to the compatible string. Core boot, I think, has some similar thing going on where they have, you can match the vendor, like the main board. So like you could say Trogdor or SM8650 QRD, along with some board ID and some SKU ID. So it's actually pretty similar to what I think we should maybe be trending towards, but it's not quite generic enough to work across every situation, and it's definitely not upstream standardized. So some of the things we want to try and do to have a unified DTP selection. We want to try and lower the effort to support new boards. We don't want to add custom string parsing that needs to get reviewed every single time. You want to go support a new bootloader. You just say, here's the ways to read some of these properties that are in your board and go match them. So you have just kind of a how. We expect hardware to provide way more information than software can care about. We probably don't care about revision 2.1 of the QCM 6490 sock. It's the QCM 6490 sock. We don't care too much. So that's more information that we care about. We want it to be translatable to different DTP packaging formats. So right now, U-boot does something different than ABL does, which does something different than core boot. And so my thinking is, let's try and make it sort of generic. Let the kernel be the source of truth. And we want to have a documented mechanism for how to match these properties. So that way, the same DTB will work whether you use it on U-boot or we use it on core boot or use it on Grub or ABL. During Plumbers last year, I was just chit-chatting with Christoph and Peter from the Google Pixel team and was talking about this MSMID stuff, and we realized, oh, well, if everyone seems to be doing this, maybe we should just try and upstream a generic way of doing board IDs. So I'm kind of in the early stages of figuring out what the design needs to look like. So this is what I've currently come up with. So you can see here that my proposal is we're just going to add a board ID property in the root node, and that can go, do one more, yep. So the bootloader can query these different values and try and do a match. So these will be magic numbers. So there's some magic number for SM8650 and some magic number, well, that'll probably just be 2. And the bootloader can query, well, what is the QCOM sock version on this platform? And it'll get some magic value, and we'll try and compare that and see if it matches. And if every property has a match, then we say, okay, this must be the right board. So if you can get an 8650 V2 with an HDK V1.1, this board is the right board. And so similarly, Pasquale, which is a Chromebook, what they're doing today is they have some compatible strings, and they say, okay, well, there's 2 SKUs that we support, SKU 22 and SKU 20. So instead of encoding that in the compatible string, maybe we can encode that in the board ID and just say, okay, well, our board is the Pascal board, and we support these 2 SKUs of Pascal. Right. So U-boot and core boot and ABL are generally all UFI based. So it'd be kind of neat, could be UFI based. So it'd be kind of neat if maybe we could create a UFI protocol in the future. So a vendor who provides some core UFI services can just say, well, you ask me what the QCOM stock version is, and I'll tell you what it is, as just a string. And so if you try and launch, you have a Google Pascal 360 DTB in your DTB image, and you're not running on any Chromebook hardware, when you try and query for the Google board, it's just not going to give you, it's going to give you an E inval back. And so this would be kind of nice to be able to really be generic, and so U-boot would just not even have a vendor-specific implementation of reading these IDs. Right, and so fit is an image tree format that kind of looks like DTB, and it encodes. It does have a selection mechanism for U-boot. You kind of describe a configuration region. And I'm thinking, well, we could just copy this board ID from your DTB into the fit image if you want, or you can read the DTB. I'm not trying to say this is the way U-boot should implement it. I'm just trying to say, we can put it in the official kernel and say, here's where the board ID is. And however U-boot or anyone who wants to generate a boot image can mess with it however they like. So we posted a couple of RFCs already, and the feedback we got so far was just go get a community consensus. So I'm trying to use this talk to present our current idea iteration and then get feedback from folks here. I think there's a pretty wide background to find out if they think this is interesting or useful, or we should just go back to the drawing board and do something that's specific. Maybe we should just say, use compatible strings, go away. So, yep. Yeah, so it's kind of a quick 20-minute introduction of what this board ID concept is. So I don't know if anybody has any questions or we want to have a discussion about this proposal. Sumit, I know you want to talk about putting it from the firmware.
Yeah, I know shipping multiple device trees is very convenient and very helpful to have the same package, software package to run on multiple hardware. And I can echo with this approach. It is something that we should do. Although, if at a point we get to the point that firmwares embed all these device trees, then that could be done at that stage as well. But yeah, at this point, U-boot can do, or any bootloader can do, just pick up device tree from the multiple device trees, basically. I agree with this approach, yeah.
So I'm trying to understand the value in describing the board ID to the kernel. Because by the time you get to the kernel launch, the DTB's already been chosen and loaded. So who are you describing this information to?
Right, so this would be to the bootloader.
Okay.
So the kernel authors a device tree, but it doesn't tell the bootloader or tell anybody this is what board it's for. Someone's going to have to know and figure out, well, the kernel authored this device tree, this has this DTB or DTBO file. Well, I know when to apply that, but it requires magic knowledge that hopefully you can read the name of the DTB file name and you can figure it out, or you just have some other system that knows what to do. It's just not a solved solution. So the goal is to try and say the kernel will tell the bootloader, here's which hardware I think it should apply to.
But talked about a UEFI runtime service or a UEFI service that could do this. U-Boot's the one that implements UEFIs, and it's also the one that has to choose. So who is it?
Yeah, so I mean, I don't know too much about how the U-Boot flow works, but at least in Qualcomm platforms, U-Boot would be probably chain loaded.
Okay.
And so, you know, you can have like Qualcomm UEFI services or some vendor UEFI services that know how to go read that, or you upstream this to Tiana Core, to EDK2, who, you know, will now know how to provide this information to every bootloader that is based off of UEFI, based off of EDK2.
So again, playing devil's advocate. Just
No,
to
yeah, this is
challenge
perfect.
you.
Yeah.
So why isn't this as simple as this SOC means this base DTB, then the board ID, this version, I look for, you know, is there a 1.1? No, well, I'll use 1.0.
Right.
Load that overlay, load the overlay for the display, load the overlay for this. And then the result has all the information the kernel needs.
Right. No, that's exactly what we're trying to solve. So how would the...
So you're trying to solve the problem of magic number to name.
Yeah.
Okay. Is it okay to solve that piecemeal at those levels that I talked about? Or do you need to, at this SOC, this board number could get different name?
I don't think I followed.
Okay. Well, like this. You got that SOC version. And you want to support those two board version numbers.
Right.
To my mind, that's one SOC base DTB and two overlays for two different board versions.
Right.
Why don't just have them both, and they can be symlinks to each other or something like that?
Right. So that could work. I guess that relies on a file system being available to the bootloader, which doesn't necessarily...
Symlink in quotes, yeah.
Yeah.
Okay.
So, yeah, I think that'd rely on an assumption of how the GTPs are packaged.
Okay. But fundamentally, you're talking about a way to map magic numbers to
this DTB
names for the DTBs. And it can be in piecemeal base and overlays.
Yeah.
Okay.
I kind of thought the bus was queried like for devices. I thought it pulled stuff, but this looks like it's for faster booting or.
No, so the buses will pull. This would be for like non-discoverable devices. So frequently you have, say, I'll give a very basic example of your display. Is generally non-discoverable. You just have to know you got to go talk to this, this address. But between different board revisions, the address that you go right to could be different. So the way you discover devices would be different between boards. Yeah, not everything is discoverable over a bus.
So the CDL is in EEPROM? Did I hear that?
Yeah.
Okay. Can you put the name in the EEPROM instead of the magic number?
Yeah, so we have talked about doing that. The problem with putting the name in the magic, the name in the EEPROM is sometimes the name will change. And so we'll ship devices to customers with a certain name, and that'll be like a code name. And then the actual part name, that this SM8650 is probably the name that the community would care about. And so we're interested in supporting devices that go through the whole life cycle. Once it's shipped to somebody externally, we kind of want to support that. In fact, we actually saw this for the X Elite halfway through the bring up, where we changed the name of the part during that. We posted patches and it said one name, and then halfway through we changed the name. That's just kind of how an unfortunate consequence of making chips.
I used to be with TI, and we had daughter cards, even Beagle BeagleBone has this. The boards you can plug onto it can identify themselves with a magic number.
Right.
And so you want to find some way to match that magic number to the overlay that you need to apply for that cape. So that's another instance of this.
Yeah, that's exactly what I'm trying to say. Let's have a generic solution so that way a bootloader doesn't have to write a whole lot of custom logic for it. We can have some sort of ABI that describes how to match that.
So even if it wasn't a runtime service, if it was a C function
it could just
that
be a
was
C function.
super portable and you could plug
Yes.
into lots of bootloaders,
Yes.
this would solve your issue.
Yes, for sure. I was just a proposal of like, okay, well now U-boot has to do even less work or core boot has to do less work. But if we want to do it per platform, that's probably how we want to start anyway, because if we like this approach, U-boot's probably going to be one of the first ones to do it, and we're not going to be able to go straight to EDK2 and say, here's this brand new standardized protocol, take it, and it's not tested or fleshed out. You know, we haven't worked out all the kinks.
So I came for the opposite problem where you have, the board knows what it wants, but you have different operating systems and you want to deliver a different DTB to each operating system.
Right.
So,
Could you just write the memory address or whatever into the memory so you pull that up and then you know where to write for your display? So instead of having a magic number, you just give the information that make it discoverable from the information in the firmware.
It's usually not that simple. So like, for instance, I'll take another example of like, say, an audio codec or an audio accelerator. ADSP might be different between two different chipsets or two different boards, right? You have some address that you want to go talk to, but it could be a completely different chip. And so it's not just simply talking to a different address. It's a whole different driver that needs to be probed. And so then that kind of gets into the territory of just fixing up your DTB, and now that creates a whole binding of the bootloader needs to know what the DTB is going to look like and know how to fix it up, and that kind of gets into a headache of fix-ups, which can fail.
So, although it's just a repetition of like my morning talk, but maybe I would just like to clarify, how do you think that the secure boot could be implemented, or how could you verify all these packaged DTBs, whether Qualcomm is going to sign them all, or whether it's the device vendors, are they going to sign them?
So it's been a little bit since I've looked in how all the system-ready stuff is going to work. So I guess I don't want to answer that directly because I don't want to say something and somebody tells me, well, you didn't get that right.
Yeah, actually, that's the problem we face when we say, I want to enable secure boot, but how we can assign like those bundles of DTBs.
Right.
Yeah.
I mean, right now they're coming from the distro, right? They're coming from the kernel or whoever's packaging.
Shouldn't they just be signed by the same person signing the kernel, right? So like, if you're packaging with the kernel, you can sign them with the same signature key that the kernel has, at least unless you're trying to use those same DTBs in U-boot, in which case there's maybe a question. But if all you're doing is taking the DTBs and passing them to the kernel, right, then if you don't trust the kernel, then like essentially the kernel could ignore whatever you gave it. And so, you know, the kernel signing key should, if anything, be stronger anyway. So in that sense, it would work fine for assigning. But if you wanted to try to use the DTBs that were packaged with the kernel, then you get into questions.
So actually, the question is not about whether it's easier to sign or not. It's whether the distro vendor or the OS vendor can actually vouch for those device trees, that these are the appropriate ones to be used for this particular hardware. Yes, you can say, I can pick up from this kernel version and I could sign them all, but do that DTB is supporting all the features that are needed for those devices.
Right, I mean,
is the kernel supporting all the features that are needed for those devices either? I mean, I'm saying it's the same level of trust, right? I mean, this person's providing you a kernel, so how do you know the kernel provides the features that were right for the hardware?
To better explain it, say for example, I'm a device vendor and you are the OS vendor. So you are providing me the OS and I want to say that this is my device behavior, how it should work with the OS or how it should work with the upstream OS. And I vouch for my device and how it should be described. Can you vouch for the device? Or like I remember seeing the EFI system partition packaging like whole of the DTBs from ARM64 tree or from ARM tree. Can they vouch for all of those device trees? That's something that was not answerable to me. Maybe you have.
I think my thought on that is just if the device trees are bundled with the kernel, then the kernel is the one vouching for them, not the device vendor, right? And so, if the device vendor can get the device trees and the driver support into the kernel, right? And they have to do both of those things. And then whoever's bundling the kernel vouches for both of those things. So the device manufacturer isn't involved in vouching for either of them, and so therefore isn't involved in signing them. If the device trees are bundled with U-boot or with the firmware, then they have to talk about vouching for them. But when they're bundled with the kernel, I think it's the kernel's vouching and the kernel's signing that matters.
Even if you accept your premise, I don't think there's agreement on what the signature for the DTBs looks like between distros. I don't think any distro is publishing a signature for the DTBs that the bootloader prepared.
Yeah, basically you need a public key that should be bundled into the bootloader. How you can verify those DTBs.
It could be done, but there's something to be decided there.
Yeah, the kernel could also just, if you can't trust the kernel, you can also just throw away whatever, the kernel could be just throwing away the DTB and loading whatever it wants. So our kind of, at least, I think Doug and I are on the sort of same page. It just comes from the kernel. Somebody packages together DTB and a bootloader and a kernel and some user space, and however you want to sign that, that's up to you. But the device tree doesn't come from some other magical place. It comes from the community, and so it comes from the same source.
I haven't thought it all the way through, but one of the things that I think about when I'm looking at your proposed solution is whether or not just going all in on overlays is maybe a solution to some of this stuff. So stuff some stuff incompatible, but then really kind of like just go in and have overlay after overlay after overlay applied to something. So you sort of say, you first apply the baseboard, the SoC level DTB, and then you get the board level overlay, and then you get the rev level overlay. And if something is specific to a given rev and a given SKU, then the overlay says, I need rev and SKU in its compatible string.
Right.
And then you sort of have a whole set of things that can be in the compatible string that says whether or not the overlay applies. And so, for instance, if you boot a Pasquale SKU 22 and SKU 20, you see that and it's just an overlay, and you just apply the overlay if it matches that. But you also start out with more basic stuff. So you start out with just the SOC,
Right.
then just the board, and then you kind of apply overlays that way. I haven't thought it through to see if it would really work, but.
Right. Yeah, I guess we'd have to, I think we sort of talked offline that the SKUs are sort of bit fields for Chromebooks as well, and that's what we do as well.
Well, I think in that case, maybe the Chromebooks would actually, should anything that's a bit field,
Right,
the
we just
Chromebook
expose it
should
to it.
actually say, Google Pasquale Touchpad A.
Right.
And so then it should start looking for Google Pasquale Touchpad A overlay and Google Pasquale Touchpad B overlay.
Right.
And the firmware would then know how to map bit 2 in the SKU ID as, touch field A versus B.
Right.
And then, so you would have to, it wouldn't work backward compatible. You couldn't just go do this to old devices, but for new devices going forwards, you could try to maybe make it more sane and go all in on overlays, and maybe it would work.
Right.
So what Doug is saying is basically what Simon Glass has proposed for U-boot fit image extensions. So the base sock would be a DTB, and then everything else would be a DTB overlay. And the firmware kind of has to produce some list of compatible strings that it knows that the board has these features, and then it will go through the fit image and look for extensions that match these compatible strings and then apply the overlays. That's essentially the extensions proposal.
Right. I guess we could potentially get into a problem where, say you have touchpad A, I'll just use yours as an example, and for whatever reason it needs to go mention some clocks and regulators, and those clocks and regulator P handles might change depending on which, say, PMIC you're attached to or which board version you're attached to, and so now you have to actually describe, well, I'm on SKU, I have PMIC A plus touchpad A, and so it can kind of devolve really quickly into, you have these really long compatible strings, and you go back to potentially back. Yeah, you go back to this, the really long.
I'd be curious to see if that happens in practice, right? So certainly I think there will be some cases like that. Like I could imagine that touchpad A and touchpad B are hooked up differently on revision 2 versus revision 4 of the board, right? And so then you may have, one overlay that says for revisions 2 and 3, touchpad A looks like this, and for revisions 4 and up, touchpad A looks like this. So you'd have to have some sort of conditionalized thing for the extensions, but I would hope that it wouldn't go past like 3 or 4 things and not up to 20, right? Because it's unlikely it's going to be like conditional on UFS and conditional on, your SDRAM part and everything. So if you just list the ones that it's conditional on, maybe it would be manageable.
Right, but firmware is not going to know what it cares about, right?
Well, I mean, but the device tree itself, if it sees, it just basically is an and of all the components. So if you see an extension and the extension lists, revision and touchpad, then when the firmware is looking through the extension, it says, well, it wants revision and touchpad. I have both of those. Apply it.
Right.
And so it doesn't need to have any smarts as long as the kernel device tree thing lists the proper set of ands in its compatible.
I guess then you lose out on that means you have to port that parsing to every bootloader you care about.
Sure. I mean, any of these things that's probably true on.
Right.
So, but if we come up with a standard, maybe it's not such a bad deal to put that parsing in every bootloader because it's a standard.
Right.
So.
So Simon's proposal is kind of the opposite. So the firmware has to produce all the extension compatibles and not parse the base DTB. Yeah.
Interesting.
And then also extensions has like dependencies. So say your touchpad A on revision 2 would depend on the revision 2 board and not the revision 4 board. Yeah.
Interesting.
That's only a proposal. Like there's no code attached to it. So.
Yeah, I mean, there's no code attached to this either because we're all just trying to have a discussion here. But yeah, that's interesting. I think generating a long list of all the compatible strings then gets complicated because if you have 5 different things, you need to have 5 plus 4 plus 3 plus 2,
Yeah, that's true.
So I don't think you need it to be in the compatible. The compatible can be fairly generic. It's the device tree content that needs to be customized. So what you end up for is some really long overlays to look for.
Right.
Overlay names to look for. And it's like, oh, I don't have that overlay. Let me simplify it to just these 2. Oh, I have that one. Let me apply that one. Oh, I don't even have that one. I just have the touchpad A. I'll apply that one. Right? So if you can come up with a mapping of the really long names to potential overlays to apply, and then simplify them out until you find a match, you can do that.
Right.
But
yes.
it comes back to this having a good way to have a directory of the DTBs, maybe symlinks and some sort of symlink-like structure,
Right.
so that you can process this quickly.
Right.
You don't want to be doing a directory search for each one of these things.
Yeah, definitely parsing the strings could take a while if they're long or, yeah.
So does this pretty much let old software run on a new board? Is that kind of what it's for? So you have your existing image that works with everything, and then you got a new board, but you don't want to update the image, so you.
Right. Yeah. So I mean, if you're, you have to have a bootloader that supports, like, right, once you've established the board ID and this is sort of settled out, once you have a new board, yeah, you don't have to update your kernel image. You would just define your new compatible string or your new board ID, and it would just pick it up. Yeah, I mean, I still kind of feel like compatible string parsing gets really complicated pretty quickly. So I'd be interested to see if there's a proposal somebody has in mind for mapping out, all these properties and to see how it can simplify. Because.
But why do you need SKU22 in the compatible at all?
Ask these guys.
I mean, I think that one thing that's a little weird is that there's no other thing to match against for device trees today, right? So we have basically a flat list of device trees, right? And then the only thing that the bootloader that's documented for how the bootloader can pick which device tree. The kernel provides all the device trees, kind of a flat list of all the device trees, and the bootloader knows what hardware it's on. It knows what its revision is, what its SKU is, and so it looks at all the device trees that the kernel provided, and it has to pick one. And then it picks one and gives it to the kernel. And so that's the problem that we are solving, right, that we're trying to solve. And that is what works today for us. But of course, you get into this complaint that top-level compatible string is in there specifically to help the bootloader pick a device tree. That's what, on Chromebooks, that's what that top-level compatibility string means. It's, hey, bootloader, this is how you pick our device tree based on what you know. And so that's actually always been kind of a negative. I think upstream has not been the happiest about that sometimes, because it means you get weird compatible strings like this, and you get listed more than one rev and more than one SKU, and you get these complicated things that we spent a bunch of time arguing with Rob and Christoph about in the past. And so, ironically, you could kind of, if you had something more like what Elliot has here, where you had some other way that the bootloader could pick the device trees among a whole list, right? Maybe it's something like a board ID or whatever. You could actually have the bootloader write a compatible string that just contained the one board that you're on. And then the bootloader, if the bootloader is no longer using that, right, like it could actually create that compatible string, and it would suddenly look more like what Rob and Christoph and the device tree folks have always kind of wanted, is to see just the board itself in that device tree compatible. And so yeah, if you had something else, right, essentially if we were on a SKU2 Pasquale, then we could figure out, hey, we match against this, and then the bootloader could theoretically write just Google Pasquale SKU22, done. That's what we're on. And it wouldn't have more than one thing there, which would be kind of neat.
Right. Yeah, I mean, another way I had kind of been thinking about, that reminded me, compatible strings should maybe be a description to the software of what hardware you're on. And so when you describe you're on SKU22 and SKU20, what if you need to do a workaround for only SKU22? Now, what do you do?
Well, then the kernel splits it into
Yeah,
two
kernel
device
has to
trees,
split it.
right? But if user space, the problem is if user space wants to know what SKU it's on, it can't use that compatible string. It has to use something else. And right now we export the actual SKU in some other property in the device tree.
Which we do too, yeah.
Device tree, if that's your compatible string, to device tree, you're declaring that you are a SKU22, which is also compatible with a SKU20. You're not on a
That's true.
SKU20,
Yeah.
according to device tree, with that compatible string.
That's what it means for anything other than the top-level compatible string, at least in the case of how Chromebooks work. What that says is I am on either a SKU22 or a SKU20. What's that? Well, what you looks like for every other device except for the top level, if you read that, you would say, I have a SKU22, and it's also compatible with SKU20. For Chromebooks for the top level one, that does not say that. This says, I am either a SKU22 or a SKU20. I could be either of them because from software's point of view, there is no difference right now. So, and that's the thing that's always been weird for that top level compatible string and something that has always made people like Rob and Christoph unhappy. But, you know, and so we could potentially make them happier if we stopped using the compatible string like that. But that is the way that it has historically worked for Chromebooks because there was no other way. So, and it's been like that for years. In fact, even though Elliot said that the U-boot method is different, actually I think the U-boot method and the depth charge core boot method is pretty much the same.
Okay.
So they both use fit image, and I think they both use the same Rev and SKU stuff, and maybe even the Tegra stuff is a Chromebook also, because there were Tegra Chromebooks.
Okay, maybe it was.
I think most of this Rev SKU stuff is all from Chrome OS in the past.
I'm going to dumb this down a little bit. I guess for those of us who don't have as much board variation, maybe 2 or 3 for a particular product, what recommendation or which method would you recommend to differentiate and select the
Right. So I mean, under the scheme that I'm proposing, you would go write an upstream thing that says, here's how you find out which revision I'm on. So you could do, you know, I am manufacturer blah a foo, and I have this property called foo, comma, whatever you want to differentiate on. And if it's 1, 2, or 3, you know, this is, you know, how you, and then you describe how to read that property. And so it would actually be much easier, I think, under the board ID scheme versus doing a compatible string, at least in my opinion. Did that answer your question?
Yeah. Also, if you're only trying to land one bootloader,
Yeah. That's true.
I mean, if you're only using U-boot, most people just code this into U-boot, right? Yeah. There's a board-specific function that reads an EEPROM, generates the name that you should look for, or the list of names that you should look for. But I think Elliot is trying to solve the problem for multiple bootloaders simultaneously.
Yeah, Qualcomm wants to put our hardware everywhere, so we want to support more than just
Yeah, so one thing that's slightly more flexible with U-boot is that your board DTB compatible string doesn't have to be the same as the compatible string in your configuration node. So you could like have some custom mapping, and that would live in some external file.
That's part of fit.
Yeah, that's part of fit.
Yep, sure.
Yeah, but we don't currently like have such an extension.
That's just because our fit image generation doesn't do it.
That's right. So you could have like an external mapping, but that only works for fit images and whatever like custom boot image format you have that could support it. So if you were like looking through the file system and just looking at the DTBs directly, that wouldn't work.
Cool. I think we're out of time, so thanks everyone for coming. Go to that one.
This reminds me a lot of browser compatibility strings in